fine? Good. Okay, so I'm Kevin Nader from 4Quant, and I'm here to present some demos. So unfortunately, because of the scheduling, the demos will come before the explanation of how Spark works and everything else. But just for a general idea, how many of you are familiar with big data and general? Okay, good. And Spark? Everyone, almost. Okay. So I guess I can assume that most of you are comfortable with that, and feel free to interrupt me at any point if you have questions about specific things that we go over. A lot of it will be source code based, and we have most of it online. So if you have your laptop with you or your tablet, you can go on GitHub and look at it, and it might make a little bit more sense because reading source code on slides is, of course, quite tricky. Skip the outline since we're running a little low on time. Basically, what we do is we do big data analytics on image data sets. And so that's some of the demos we'll show today because I think they're more exciting than a lot of the other big data sets that typically get operated on. And so this varies from looking at weather patterns using synthetic aperture satellite images to stitching together tomography data sets to look at a brain at full scale to trying to identify cancer and sort of other similar problems. And basically, there's a number of us that work on it, and what created it was really the need based on the amount of data produced at the Swiss Light Source, which is the research institute I did my PhD at. So the problem we, of course, came into was that the time breakdown for scientists was sort of falling apart, that people were spending almost all of their time doing IT tasks rather than focusing on what's actually of interest, and this is where big data comes in. So here is kind of a simple example where each one of these gray boxes is a for loop, and this is the task of stitching together 56 terabytes of data, and that each one of these for loops, of course, takes a long time, and when they're all inside of each other, that then means that you have to wait with one machine for weeks to get your result. So the super workstation that we have, if you try to process it on there with 40 cores and a really good graphics card and everything else, you wait 40 to 160 days per iteration for it to finish running. So, of course, that doesn't make sense, and dealing with data at that scale is quite challenging. So this is where you use cluster computing and cloud computing. It's kind of a basic. So many of you are familiar with this, that you have kind of the user, the driver, the master, the workers, and then somehow storage connected to all of this. So with Spark, all of this is kind of handled for you, and if you do it with IBM Bluemix or some of these other offers, then you can quite easily integrate their services so that you don't have to handle these tools yourself. And so here we show basically the advantages of using it, because if you don't use these kind of tools, you spend all of your time worrying about message passing between different nodes, and this is then very inefficient. And of course, this can get incredibly complicated, and this is just a very basic task that's being shown. Particularly with image data, you then have a bottleneck when all of the machines are trying to read images off of one place at the same time, that it goes very, very slowly. And so this is where object storage and tools like HDFS, so the Hadoop file system, solve that by moving the images closer to the computation so that you can load the data much easier. So I'll leave this out for now. Of course, the definition of big data, which most of you are familiar with. And a little bit about Apache Spark, for the ones of you who haven't heard about it. It's the fastest terabyte and petabyte sorting tool in the world. And so even though it's written in Java, which isn't always considered to be the most efficient language, it has the world record for sorting this data. So for large processing tasks, it's unbeatable. It also has sort of the scalability of being able to go up to thousands of machines, and the fault tolerance, that you can have 2/3 of the machines crash and your task still finishes. So this is a little bit more about kind of our tools, where what we've built on top of it, and a little bit we'll show off today. Here's kind of a more detailed view of what Spark looks like, and the components that we'll focus on right now are really these streaming components and then this GraphX. So has anyone used streaming before? Spark streaming? And GraphX? Oh, no, two. Okay. Good. So here's sort of the basic outline for Spark, that if you want to load all of your data sets in, you basically use one command to do this. In this case, this is image data. For text data, you use text instead, and for synthetic data, if you're doing simulations, you just use the parallelize or the random number generator, which allows you to come up with data sets quite easily. And then you have sort of these different operations that you perform on the RDD, which is this resilient distributed data set, in order to complete your analysis. So yeah, this then shows if you have lots of different data sets spread over different sites or different types of storage, you can then easily combine them together so that you have everything in one simple table, which is what Spark SQL allows you to do. So here, you see the setup that you have for the standard queries, the distribution and analysis. You can have thousands of nodes connected, and you don't have to worry about the organization. It's all handled for you. Now here's the sort of real-time Spark streaming, and the example we'll use that with is the webcam on my computer. And so this one's being run locally, but you can do setups like this in real time as well. And so Spark isn't really a streaming tool. What it does is it does micro-batching. So you have a ton of data coming in, and you break it up into small little groups, and you analyze each group separately, and then you indicate what sort of connections have to happen between groups so that you can do the analysis that you want. So here, the basics for the streaming analysis, you have to create a webcam receiver. So you have some sort of channel that you use that provides constantly new data sets. And so Spark offers integrations with Kafka, with a lot of these other tools. And for this, we created a special one for a webcam, which can then be directly integrated to the Spark streaming context so that you can run the analysis. We then use our tools so that you can use ImageJ on top of it. And so we see the first step that happens to it is that you run a median filter, and that kind of blurs out the objects you see in the image. The next steps, you create a background image. And so what that does is the median filter looks in space and sort of smooths out everything you see. The background image looks in time. And so smooths, averages the images together, and this then makes it possible to start to look for outliers. So because it takes a little bit to start up, have it run now, and hopefully it works. Are there any questions thus far? Of the results. And here's the median filter, and then the outlier detection and the time filter. So now the median filter you see is a blurrier version of the image that we have here. And the time filter then averages a number of time points together. So if we cover this, for example, the time when you can see my motion together, see the median filter, and then it's reflected on the time filter in the next image. And so all of these images are coming in. They're being grouped together into small micro batches. Each one of the micro batch has all of the images inside of it processed with this median filter, so that you kind of get rid of the noise and small variations. And then you have the time filter, which shows you sort of a time-averaged version of the image. And then this can be run sort of continuously. We then have the next steps on the analysis, where once you've created this background image, you want to somehow identify if there's an outlier present. So with images, this is fairly straightforward. You take each image, you then take the background image that you've calculated, you subtract the background image for it, and then you take the mean value of this difference. And so if the mean value is above a certain point, we define this here as 20, but you can change it to whatever you want. And with Spark, you have the advantage of having sort of an interactive console where you can type everything in. You can then get different results as your outlier. And so if we go back here, see the outlier images, and this has been a subset of the images where the change, the difference between the foreground and sort of the background was large enough that it considered it to be an outlier. Then have these curves. Yeah, here you have the outlier detection score, so you can kind of see with time the events that really fell out. So that was where I covered, here was where I covered the camera with my finger. And then you have a large outlier event, which is caused by that. So what's nice with all of this code and the way that you write it here is that you just write what the process is, and it handles distributing the code and making sure that it runs on all of the images that come in. And so if you're running this on a number of machines and one of them crashes, it automatically sends the images that haven't been processed yet to another machine so that you can get those results. Is that clear? Any questions about the streaming stuff? So there's a demo of this on YouTube if you're interested in watching it in more detail and looking at the curves. But I think you guys get the point more or less of what's going on. And you can see the other events here that have been created from that. And so with one webcam, it's not very interesting, but with many different webcams, of course, the processing task is very difficult to keep up with, and so you can take advantage of cluster computing to solve that. So nice here is you can then see in Spark what jobs are actually being run, and if you're keeping up with the computation that needs to happen. So here you see constantly new data coming in, how long it took for each processing step. You can then click on one of these, see the minimum time, the median time, the maximum time, and how long was spent in sort of the different stages. You can also see for this that it's been running for 4 minutes and 48 seconds, and it's done 433 records and 46 batches. And so each batch has been 6 seconds long, and it takes between 3 and 7 seconds to process. And so, of course, if it's a 3, you can keep up with your stream without any problem. As soon as it gets up to 6 or above, then you can no longer keep up with it, and you have a major issue streaming the data that you have. Kill that for now. Go back to the slide. So, again, no one has used GraphX before. So to switch over to the GraphX demo. If you're interested, you can go to GitHub/4quant and look at the Spark FEM demo, where all of the code is available, and it will eventually be published as a Spark package so that you can easily incorporate it into the notebooks that are existing there. And basically the idea for finite element modeling and using GraphX is that a finite element model, or one of these lattices, is really a graph. And if you have a large amount of image data, one of the common things you do with it is to simulate it with this finite element models to understand better what's happening inside your data set. So to see how it reacts to certain sort of forces acting on it, or how strong it is if you try to bend it, and other sorts of examples. So finite element is fairly basic. You look at each one of the boxes that you have, and you basically say that the force on this box, the sum of all the forces that act on this box, is the mass times the acceleration. So sort of high school level physics. And this fits well with the GraphX model of systems because you have vertices, which are each one of these boxes that you have to fill. And then you have the edges, which are the connections between these boxes where you have information being passed back and forth. And so basically, the model that you have is that the force that's put on each one of these boxes from the neighboring boxes is this spring force. So you have Hooke's law, and you look at the distance or the length of the spring that you have and the resting length. And so if you start stretching it, then it wants to return to the original position, and if you start compressing it, then it wants to return, so it kind of always acts in that opposite direction. And so from that, we can create these case class types in the data set. So where we have sort of the coordinates, which we call D3 int and D3 float, for 3D positions as integers and floating points. You then have the image vertices, which are points that have an index, which tells you which vertex you're at, which vertex you're at. And then you have a value, which in this case is an integer, but you can also have other values. So in the case of bone, this value could be the calcification density, which will then have an influence when you start to stretch or move the different points at how large this K returning force would be. You then have these edges, which are connections between the 2 points, and then you have a force edge, where the edge itself exerts a force on the point, and those are the kind of basic classes that you have. We go through here. You can then see in the project, you have this types folder where you have all of the types defined, and then you have different operations which exist on them. Check this all out yourself and make modifications to it if you're interested. But so basically you end up with all of these different boxes. You then have forces that act on these different boxes, and their position gets updated. And so it's ideal for Spark-like processing because you have iterative approaches. And so if you use something like Hadoop, then you have to reload the data for every single iteration. And here you can keep all of the data in memory, even if you have a very, very large data set. Of course, there are much more specific tools like PairFE, which have been developed for supercomputers, but these are then hundreds and thousands of lines of code, which spend time sending messages back and forth between machines because you divide up your images into chunks. And here we see we can get the same sort of, not performance, but the same idea implemented in rather few lines of code, which means it's very easy to see what's being done and make modifications to it. So here's just the types that we have defined. You can go down into the functions which are here, where you can turn an image to a graph, where you basically just create the edges by looking at all the different neighbors around each point, and the vertices by taking all of the image points that were originally present. You then calculate the forces at each point using that fairly simple piece of code because you just have to subtract these two 3D points. And you can then sum all the forces together at each point using this MapReduce triplet. And so rather than having hundreds and thousands of lines of code, you're able to implement a fairly complicated process using just a few simple functions and then scaling up to many computers if you need more performance. Here's where you then have this iterative approach because you move the points, and when you move the points, You then need to recalculate what all the forces are, and so you take a very small time step, and you just iterate hundreds or thousands of times to see how your data evolves. So here's where you can then say, this is your time step, this is the number of steps you take, and these are the commands you run. Here's sort of a slightly more compact version of this code, but again, you can look at it all yourself, which is probably much easier than trying to understand it from these points. So yeah, you can have one iteration, and one of the nice things about using Scala is that you can then make a domain-specific language out of it using these implicit types that it has, so that rather than saying val, femgraph, 2D, you can just have very sort of almost English-like sentences where you have all the commands together and it generates everything for you that's necessary, so that you can have a very understandable code base rather than being lots of complicated functions. I have this open here. This was just one of the demo samples that we have, where you load the data set into one of these Spark notebooks. And so if you use IBM's services, you get this as part of the Apache Spark Starter Kit. You can also do it yourself and download Zeppelin or Spark Notebook. I don't know if anyone's using those tools now. But what it allows you to do is kind of execute the code interactively and change the parameters and rerun it. And then what we have here is we expand it to a Spark SQL database, which then allows you to plot the data and play around with it, so that you can then see for all the points that were in this bottom left corner, how did it change with time. And so the point started off here, and it collapsed in that direction. So each time step it moved a small piece inside there, and you can change the points you look at. So here's where you show them all the points, and then you can see some of them on the edges moved quite a bit, and the ones in the middle didn't really move at all. You can change the time to show the size instead of color, then the points get bigger as you move later in time. So with these D3-based visualizations, you can actually play with your data as easily as if it were all inside an interactive program. And so this is a fairly small data set, but it could just as easily be hundreds and millions of points, and you just take a small subsample of it to preview it to see how your results look. So, are there any questions on that? Yeah. If we benchmark this running on a single node, yeah. Yeah. So with the commands that we showed in their very basic form, it's not extremely efficient with the operations. What you need to do to have it run well are use sort of these space-filling curves, which is also what they use for this GeoTrellis project. I'm not sure if you're familiar with that. But basically it partitions the data such that all of the points that are close to each other are on the same machine. And so if that's the case, then you only have this communication across the border, which means your performance is still quite high. You're always going to be somewhat limited by that, but you don't but sort of the benefit you have is you don't have to spend a huge amount of time dealing with this exchange of information on the border, which is what most FE codes spend all of their time doing. Right. Right. So like the example of that would be sort of this Z curve, where you sort of zigzag through the data set so that you have all of the points that are close to one another on the same machine, and then all of that processing happens on the machine before you have any exchanges take place. With this program, no. With some of our image processing tools, we do, but with this one, unfortunately, we don't. I mean, I would guess the parallel optimized codes are faster, but this just makes it much more flexible and much easier to play around with. Yeah. Oh. Yeah. Yeah. I mean, if you have the partitioning, then they're fairly localized, at least from one iteration to the next. Of course, many iterations, you have it spreading, and so you have more of those problems. But if you look at page rank algorithm, each page is connected somehow a little bit to most other pages on the internet, and that's still wildly parallelizable. Well, but this one, the points are just connected. I mean, the lattice that we sent up, they're just connected to their nearest neighbors. So you don't have points connected all the way across the grid. So it's actually even a better defined neighborhood than you have with PageRank. The clustering should be easier, or partitioning should be easier. But yeah, we should do benchmarks to see how well it actually. Elaborating on programming in Scala versus Python as related to Spark projects. So we've done everything with Scala so far because it has the type safety, which makes it a lot easier to develop larger projects and sort of group everything together without having to test it as much. With Python, you have to test everything very thoroughly to be sure that it still works. And with Scala, you have the benefit that there's no sort of shuffle back and forth or serialization step back and forth between the Java function and the Python functions. And so with Python, it works very well if you use the DataFrames and you use some of these other tools that are built inside of it, because then you're just using Python to orchestrate. But when you use Python to actually process, you then pay for each one of these operations that take place, because you need to copy it from the virtual machine into Python and then back again. And that translation, depending on what you're doing, can be quite expensive. Yep. So for image processing, if it's possible to run on a cluster of GPUs instead of CPUs, you can. The problem that you run into is that you then sort of have this barrier between CPU processing and GPU processing. And you can write all your CPU code in Java, and then your GPU code is in another language. And so if you use something like this linear algebra library MD4J, you can then take advantage of GPUs for those specific algorithms. But for everything else, then you need to implement the GPU code yourself. And so it's possible to do it, but if you have very complicated tasks, it can be messy to copy the data back and forth, and you lose a lot of the ease of use that you have in developing in one environment. So for deep learning, it's one of the things that they do, because training these convolutional neural networks is much faster on GPUs. I mean, orders of magnitude faster, and so you really have a huge performance gain. For a lot of the image processing tasks, your bottleneck isn't necessarily the CPU time, and so for that, then rewriting everything for GPUs doesn't necessarily make sense. But no, I'm done. Are there questions in Vienna or Berlin?
Okay, are there no questions in Vienna or in Berlin or in the virtual meetup? Okay, so then we will do a little slight agenda change because we are a bit running out of time, so I will just present my stuff very, very fast now to give David the stage later, so that David really has at least 1 hour. And yeah, so we have to switch laptops. We should take the video. Yours. So again, here, I'm Romeo. Welcome to the Advanced Spark Meetup. And one thing I have to say sorry to the people in Berlin and in Vienna. They asked us to repeat the questions because they didn't get the questions. So I will ensure that the questions are repeated and that I will remain close to the mic because the audio quality is not so good in Berlin. So sorry for that. So what I want to show you very shortly is we have a Apache Spark service in our cloud, and that is what Kevin mentioned, and he's running actually on this service. And the cool thing is about this service, it's running in a free tier, so everybody can use it for free, and we have 50 GB of storage there to use it. And I will just show you one thing. So if you want to use that, you can go to this URL, and that's what we have in the free tier. So that's 20 GB of HDFS storage, 50 GB of Apache Spark storage, which is in OpenStack Swift. We have also CouchDB, MongoDB, and a lot of other services, Elasticsearch, Node.js, PHP, Java, whatever you can think of, because it's an open cloud system for platform services. In addition to that, we have a startup program where Kevin also is participating, so he has $2,000 to spend on our cloud. So if there are any startups in here which are less than 5 years old and make less than $1 million of yearly revenue, you can come to me, and you will get between $24,000 and $120,000 from us to spend on our cloud. This can be platform services like Spark, but also on pure bare metal infrastructure or virtualized infrastructure. one thing I forgot by seeing Alexander from AFNet. AFNet is the sponsor of this meetup here in Zurich. So all you will drink later is going on his bill. And I will just show you very briefly and fast how that works. So you take this URL, you register. It's 1 month, you get everything for free, and after that you end up in the free tier, which is described here, and it will look a bit like that. So you will end up here. That's the main screen of the IBM Platform Cloud, which we call Bluemix, because IBM is blue and we mix there everything in. And if you want to create a Spark Starter application, you click here on Create App. And because the cloud supports virtual machines and it supports Docker containers and a lot of other things, but I just say create application, web application, boilerplate. By the way, I'm recording this session, so you can do it later in a not so fast way. So you click on Spark Starter, and Spark Starter is a composite. It consists of 3 services. One is a runtime container, and in that runtime container, it's running a Python environment, which runs the Jupyter notebook, which Kevin mentioned. So you can either use Jupyter or you can use Zeppelin. And Zeppelin, I don't know why they even started to create it, because Jupyter, in my opinion, solves all the tasks, because you can implement or use it with any programming language supporting that kernel interface. And there's one for Python, which is called IPython. There's one for Scala, which is called iScala. But anyways, Zeppelin is from Apache and Jupyter not. So what I do here is now I give it a name. So I say Advanced Spark Meetup Zurich, Berlin, Vienna, and Virtual. Whatever, that has to be a unique name, because it will immediately end up on a public URL. And, I didn't do that, sorry. I have to... I thought this is the correct one. You have to enter the host name, and then you enter, say, create. And I've done this. This will take around 3 to 4 minutes, but I've done this before. And it will look like this. So it consists of this Jupyter notebook running in an application container. Then it consists of the Spark service itself, which is an open source Spark implementation, so you can access it from outside using the normal Spark REST API. And there is an OpenStack Swift service, which is used for storage here. You can also use it in conjunction with HDFS, but this boilerplate here, which I'm showing, is currently supporting only Swift. So I'm a bit of struggling with the network, but wait. So in this view, I'm seeing everything which is running in my account, and I have just started this one here. And this basically brings me here to this container where the Jupyter notebook runs in, which supports iScala and IPython, and then I have this object storage, and I have this Spark service itself. So if I click on this link, this URL which has been generated for me, brings me to this Jupyter notebook. And what I will do now here is I will just create a new Scala notebook. So it uses a iScala kernel, and I can interact interactively with Scala and the Spark service in behind. So what I do now here is I will just run some code from a tutorial which a colleague of mine has written. And I don't think I will continue it until the end, because I just want to give David more stage. But the thing is, you can add external jars to the system, which I do here. So I Control V. I go back to my notebook. So I say enter. Oh, and then I have to run it. See, that star means it's actually processing something. And now it downloads this jar from GitHub. And now it's part of the runtime environment. here. So I will continue with this. So this actually implements a Spark application written in Java, and this I have already prepared because you have to enter your Twitter credentials from the Twitter API and some other credentials from another service, which I'll explain later. But the thing is, it should be somewhere there. Oh, it's done. Oh my God, it's done. Where I have put that. Okay, maybe then I skip that. So the thing is, you go to Twitter and you go to dev.twitter.com. You go on the top bottom right side, you will find something like manage your application. You have to create an application and you will obtain Twitter credentials there. And you can put them here. And the other thing is the Watson endpoint. Since we are in a platform cloud environment, there are a lot of different services, and one category of services are the IBM Watson services, which are cognitive services, which basically expose their service at the REST endpoint. And in order to obtain the credentials, you have just to follow this script, but the credentials I have already obtained for you somewhere. I have to just double check. Services, and I go to Watson. So that's, for example, it's a sentiment analyzer as a service. So you send your text and you get a complex JSON object back, which basically defines or gives you measures about the text. And here you see it's very simple. REST API, so that's the API endpoint, the username and password. That's HTTP basic authentication, which I'm using here. And I have just created here, that's an online HTTP request tool. So that's actually issues a post request to that Watson service and uses here the basic authentication credentials. And I have to set two headers and a bit of payload, and then I get back this complex JSON structure, which actually gives me measures about sentiment and other psychological scores of the text. And that's used by this service. So I have just prepared this already, and I have to show you the prepared notebook. So give me 1 second here. That's here. So I go back to this one. And I think it's here. Yeah. Here are the credentials. So let's see if they are still valid. So I don't do the download again. And go here and I have to do the download again. Okay, let's do it again. And then okay, now it looks better. So actually this Spark application written in Scala just obtains tweets from the public Twitter API and stores them in a temporary table. So that's very easy in Spark. You can create a temporary RDB and this resides in memory. You can correct me anytime I'm talking bullshit. So the thing is, this application also incorporates the usage of Shark, the SQL engine on top of Spark, which can be seen here. And what I can do now is I can query against the tweets, which I will do here now. Let's start from tweets. And then you see I get the tweets. And the thing is, there is currently a defect in that Watson service because the Watson service I'm using is in the experimental section. So we have stable and beta and experimental, and it currently returns 0 for all the results. That's why I actually cannot show very sophisticated analytics on that. But what I will do anyways is I will write all that data. Already exists. Okay, let's say 2. Or it doesn't matter. You can believe me it works, but I just executed that. You believe me that it works. So I will write all that Twitter data, which I've captured now to a Parquet file. Parquet is a binary format for storing such types of data, and that has happened here. And now what I can do now is I will create a new notebook in Python, because Python can use a library for plotting graphs in Jupyter, and therefore I will create a new Python notebook. And what I will do now is just run a couple of examples, and then I will open up for questions, and then I think we have really 1 hour for quiz. Give me 1 second, please. So now let's move fast forward to the Python stuff. So that's the Python code. So we just believe that this works, and go back to my Python notebook. Is that that's my Scala notebook? Where is it? Done. Let's create a new one, no worries. So, it was here, sorry. So I will take the Python code here, I will execute it, and run it, and it will load the data from the Parquet file, from the Swift storage. And the Swift storage, for those who don't know, that's the equivalent to Amazon S3, but in an open source, open standard fashion, coming from OpenStack. And that's also part of the Open IBM Cloud. So you can store any amount of data in the Swift storage. And we obtain the Shark data frame now from this Parquet file, which we can now use to work with. And I will just close a lot of stuff here to make it more easy for me. And just go to this one. And now we will do some SQL-based analytics. And only we go to the first plot, and then I open up the questions. So since we do not have any sentiment scores, this line here is equal. But if you would have sentiment scores, you would see something like that. And starting from that, you can just continue this tutorial. Okay, so if you want to do it yourself, again, here is the link, and I will post the tutorial later into the Meetup group. And if you're interested, you can do it. You can always contact me. My name is Romeo. I'm a participant in all the Meetup groups, and I'm open to any questions there. And now I open for questions in Zurich. So are there any questions? Comments? No? Okay. What about Berlin or Vienna or in the virtual session? Is there something I can answer? Okay. So I think we take now like a 3-minute break to connect the other laptop, and then we will continue with the advanced stuff. Say in 2 or 3 minutes, I'll call you people in again. You go out here. Yes. Then you just go left until you hit the wall, and a bit of left, and you will see. So for everybody online, we will continue in 2 minutes with Chris from the Spark Technology Lab in California. And I just repeat, I don't repeat it. I think you know about the sessions. It's on advanced Spark stuff, and he will be there in just 2 minutes. We just do another audio test. I think in Berlin they have a problem. So how is this? Can you understand me? Okay.
Clearly. Okay. Hello. Make sure we can see everything here. All right, so it's 10 after 7. How late do you guys typically go? Because I've got about 2 hours of material, so I can talk. You guys want to go for an hour? Okay. Yeah, I mean, all the slides are posted. Actually, I just posted them. All the slides are on slideshare.net. Yeah, this is the link here. The latest SlideShare will be the one posted. So if you guys want to take a minute to load that up, that's cool. Okay, Yeah, the name of this talk is called Spark After Dark, something I had created about a year ago. I came from Netflix, right? Like, you guys have Netflix here? I think you do now, right? Yeah. Right. Like, when did you guys get it? Did you get it just recently? Oh, really? Okay. It's been that long since I think the last countries we did were Norway, Sweden, when I was there. So is that about when you guys got it? Was it around that time? Or was it maybe, it's probably after that. Yeah, so basically I was tired of doing movie recommendation type stuff, and I wanted to kind of branch out and do something different. So I found this dating site, data set that had about 17 million records. It wasn't huge data, and it's totally anonymous, and it's I think a Czech dating site or something. So yeah, it was kind of interesting. I started playing around with it, sort of sparked a couple ideas where maybe I could build something that would be fun for like a crowd to do, big conferences or meetups, things like that. So I think we're going to actually start with that, just because I've been doing this talk for the last couple of weeks, and I'm getting kind of tired of the order in which it goes, so I'm going to subject you guys to some different ordering. My name is Chris Fregley, Principal Data Solutions Engineer. I just joined the Spark STC, as we call it, Spark TC about maybe 3 or 4 months ago. Came from Databricks, which is the company behind Spark. They're about 2 blocks, in San Francisco, about 2 blocks away from the Databricks office. So it actually works out well because the Spark Tech Center is 2 blocks closer to my house. So it's like 2 blocks less of a walk, which is why I have the belly, I think. Yeah, plus all the beer I've been drinking out here in Europe. Yeah, there's a picture of my mom right there, my first day at Netflix. Moved from Chicago to California, to work for them. I did about 2 years there, and then did 1 year at Databricks. And once IBM made the announcement, it was pretty compelling announcement, right? I mean, I could do this kind of stuff and get paid. I had the Meetup already, so they were pretty excited about that. I just kind of slapped IBM's name on it. So, I started this Meetup, the Advanced Apache Spark Meetup, I think back in June, maybe July. And the whole goal was to try to do something deeper and more interesting than just the regular Spark use cases. And although that use case was pretty cool. That's the first time I've seen that. The image stuff was pretty cool, that first talk. So, but my goal was to really get deep and go sort of code level. And I was a bit concerned about this because it's still pretty early. But, I mean, it's San Francisco. This is where everything's happening. So, fortunately. Yeah. Should I do... Because I could do the slide share. Yeah, so right, so that'll show up, right? So let me do... Oh, yeah, of course. Okay. Slide share. Can you guys see it? Hey, can you guys see that? So just to keep talking a little bit, this meetup, it's already at about 1,500 people in just the last few months. So I was pretty excited about that. I've gotten a lot of good interest. People really appreciate the level of depth. There's been a couple places along the way here, in Europe where people didn't appreciate the depth, so it's tough to gauge until I, get home and read the comments, and people have no idea what I was talking about. So, so we're going to have about 4 or 5 pretty deep demos, and then all the code's available, right? So there'll be links to the GitHub and everything. And I created this Spark After Dark, right? There's also this code term called flux capacitor. I bought fluxcapacitor.com about 15 years ago and did nothing with it, for 15 years. So finally decided to repackage it, especially with the, this most recent thing going on with, the movie Back to the Future, and I think this was the year, October or something, 2015, where they went ahead. So, was it? Yeah, 21st. Yeah. Oh. No. Yeah, so just a quick poll, right? It seemed like there's actually more people here that are doing Spark than I thought. This is definitely the highest concentration I've seen so far here in Europe, which is pretty cool. But who's actually using this in production, right? You guys actually using it? Yeah. I decide just kind of tinkering. Okay. Spark streaming, Spark. Just get a quick hint, Spark streaming. It's pretty much everyone using Spark streaming. Yeah. Spark SQL, I assume. What else? Any MLlib, any Spark ML, any GraphX. Yeah, how about things like NL, TK for the NLP stuff, and scikit-learn from a Python standpoint? Okay. Yes. Are you guys actually contributing back any machine learning libraries? Yeah. Right, do you guys know about spark-packages.org? It's the absolute worst domain name ever, but I guess sparkpackages.org was already taken, and the guys at Databricks really wanted Spark packages. It's kind of I call it a 1.5 class citizen to Spark. It's not quite a second class citizen, but it's where a lot of things go that don't make it into the core, right? And so the machine learning libraries typically end up there because everyone has their own data set that their own machine learning library is awesome at, but from a general standpoint might not be the best algorithm. So check out Spark-packages. There's a lot of things out there locality sensitive hashing, right? Ways to bucket things so that you can find similar items in parallel, things like that. So check that out. There's a whole ton of Spark SQL data sources, right? So DataFrame data sources. So Avro is out there, CSV is out there, Redshift, Cloudance. We're working on DB2 right now. Of course, Big SQL, some of the other IBM stuff. All right. Yeah. So, I'll just keep talking. Yeah, I came from, let's see, where did I start? I have a chart on where I started. I think I started in London. Yeah, there were quite a bit of people there that had advanced questions and everything, right? So that was cool. And then Scotland was a little dismal, a few other places around there, things started to kind of trail off. But, I didn't know when I came out here. I just picked cities I wanted to go to, honestly. And, I don't know if my boss knows that, but he's probably watching right now and does now back in San Francisco. But and like I said, some places I've been kind of tailoring this talk, to either be more advanced, to be less advanced, but I think I'm just going to stick with the regular, level of detail here. The cool thing too is I've sort of made it so that just general computer scientists can understand it, so it's not necessarily, Spark, not necessarily even big data, but in fact, some of the Project Tungsten stuff, that's all about low-level optimizations, right? The whole thing there is you're going to operate on serialized byte buffers. So, bring it back to, we've all done this. Every 10, 15 years, we always go back and rewrite our own, garbage collection and all that stuff. So, that's exactly what they've done with Tungsten. And there's sort of tedious manual process to that. So, like specifically with Spark SQL DataFrames, there's about, I don't know, right, like 100, 150 UDFs that are pretty common, right, like standard deviation, average, all that stuff. And they've gone through and actually rewritten those to operate on, right, like byte buffers. And like the whole saving there with Tungsten is so that like you don't have to deserialize the object and then compare it. Right. So think of a shuffle sort, like a sorting type of use case where you want to compare two keys. Right. Yeah. So the ability to actually compare two serialized buffers is hugely valuable. And then also compress buffers too. Right. So there's compression techniques like LVF where you can actually change order. So you can actually sort, right, like without ever having to deserialize or decompress. So, yeah, stuff like that's kind of cool. And that's my talk. Yeah. All right, so should I stay in the browser? Okay. No problem. I can't full screen, though? Is that going to screw things up? Well, that's unfortunate. It stopped moving, though. So, yeah, can I try it, or will it screw it up? I just hit it back. I didn't mean to do that. I'm sorry. Quickly. Yeah, did you see it? Oh, really? Okay. All right. So, yeah, I think the two big topics here are the fun one, which is Spark After Dark, which is the like dating site kind of thing that I built, and then Tungsten. So it's going to be fairly high level. It's still detailed, and then it's going to be low level stuff. So let me. I don't really know where I am in the presentation here. All right. Yeah, and then one more thing. I've got a book. I hope it's coming out next year. Yeah, who knows? We'll see. These books take a long time, and then I keep like having to rewrite chapters every single release. So it's like at some point, these presentations are kind of a historical book. Yeah, these are the cities. Let me just kind of give you guys a quick. Right. So obviously Amsterdam. That was kind of where everything was happening. I think there were about 1,000 people there. What was interesting is that Databricks had provisioned, I think, for about 800 or 900, and like typically the conference sells out maybe like the day of or the day before. Like they're usually pretty spot on, but here they just got blown away. I mean, they like physically couldn't get enough people in there, which is cool. I don't even think my boss had a ticket, so I had to kind of like stand outside and I had to give him my pass and stuff. So let's see. Yeah, and then I guess, I'll be going to Geneva also, and then back to San Francisco, and then do one more stint in the Nordics to watch a little, right, like Netflix from up there, since I don't even have Netflix anymore. Right, they took away my free accounts, and the $6.99 or $7.99 was just too much for me to handle. Yeah, also there's the Strata conference, right? Like, have you guys been to this Strata conference? It's kind of I think it used to be called Hadoop World or something like that, and they merged. It's an O'Reilly conference, so yeah, there's always a lot of good stuff there. So yeah, I'll be heading out to Singapore. Okay, so what is Spark After Dark? I'm not going to spend too much time on this, but right, like, have you guys ever used Tinder? Right, like, do you guys have Tinder out here? Yeah, that's one thing I've noticed about Europe is that Tinder is the only dating app that I've seen consistently, like across every single country, even Scotland, everywhere. I went on one date, but that was with an American girl that was in like Madrid, and yeah, it was pretty funny. We were just making fun of everyone. So yeah, because neither of us really speak the language. All right, there we go. Yeah, so this is the GitHub link, github.com/fluxcapacitor. There's a whole ton of stuff going on. This has been going on for about a year. I didn't just do this like this weekend or anything. We'll dissect this flow. It's sort of an end-to-end pipeline using Docker is kind of the container. That's the unit of transport. All the demos I'll be doing are running on a single software instance. I just pull down Docker, pull down like the image that you can find off GitHub, and really get it going. So we'll go through this entire flow too. So there'll be like a nice UI. That's the upper left, and then it's going to go through Kafka, Spark Streaming. We'll go to Cassandra. We'll use like Zeppelin and pretend that we're data scientists and actually run models. We'll deploy the models. I'm using like Elasticsearch, not for any reason. I just wanted to try the Spark Elasticsearch connector. So I got that going. And then back to the users. So we'll actually generate like recommendations for this group, like based on what like this group chooses. Okay. Just real quick, themes. My favorite one is just be nice and collaborate, right? Like the best people I've learned from personally. This is my little preachy moment that I get to do because I get invited to stuff, but this kind of stuff, this is what makes the Bay Area so good. There's like a million of these things every night, right? You can go like the whole week and eat pizza and eat, drink beer and get fat just off these meetups. But so some of the more technical ones, filter early. So it's kind of a blanket statement, but it's not necessarily so obvious, right? Like before you join, filter as much like data down as possible, right? And then filter deep. So this is like the ability to actually filter in like the actual data source itself. So like within Cassandra, like within your file system, choose file formats that support partitioning, right? So you can filter. Because like the less data that you're pulling across, the less data that you're moving between nodes, right, the better. Things like approximations. Yes, I mentioned like locality-sensitive hashing. So these are ways to not necessarily get the exact number, but sort of approximate. There's things like count, min, sketch, hyperlog, log, bloom filters. Seem to be pretty like well known, where you're not getting like an exact answer, like you don't know for sure, but within 5%, 10%, something like that, maybe you're okay with it. Huge savings with these big data workloads. Like trying to minimize random seeks. So this applies from a Tungsten standpoint. This applies to memory. Right? This is like in-memory buffers and like CPU cache lines. Right? Don't do random stuff. Don't start dereferencing pointers everywhere. Right? Because that's just going to keep clearing the CPU cache line. So I'll actually show a specific example of that, where we're going to do matrix multiplication sort of the naive way, right, where you're clearing the CPU cache line, and then like we're going to be thinking about the CPU cache line and like do a matrix transformation and go both the same way. It's huge savings. So the sort of opposite of that would be to maximize scans, right? So once you actually get to what you're looking for, maximize how much you're going to do from that point on. So from a hard drive perspective, just think of the mechanical sympathy, the term mechanical sympathy of this, where the disk seeks to one place and then just rips across and does all of your aggregations right there, right? So columnar file formats like Parquet, like Orc, things like that store data, that store all the columns together is super powerful, right? Because that's typically what you're doing here, right? Like you're doing a lot of aggregations, you're trying to find standard deviations, trying to take all the column data together. So by physically placing that on disk next to each other, it's huge. So go off heap when possible. So Tungsten by default, you aren't going off heap, right? It's using byte buffers, but they're all still on heap. And I think that's kind of it's sort of an evolutionary thing right now. People can reason about how much memory they have, how much memory that they're allocating. But once you flip that switch, which you can with Tungsten, you can say off heap equals true. Now you're separating your data, right, from your so there's one fixed JVM heap, let's say, that you're sticking with the 30 gig heap, because of Java limitations, things like that. So by splitting off your data into a separate byte buffer that's off heap, right, like now Spark or like MapReduce, whatever, has the ability to use all of that 30 gigs for like its own processing. So yeah, kind of obvious, but so we'll talk a little bit about that. Sun actually gives you a way to do, there's this unsafe operator, or this class. It's kind of like JNI, but it's not JNI. It like lets you like allocate like first class byte buffers. But then all garbage collection, right, that's up to you to do. So yeah, and then parallelism. Something right, like with locality sensitive hashing where you're splitting up, let's say you have like 50,000 rows, and like picture a big matrix of users and then movies for like a Netflix case, and like you're trying to find similarities between those users. So if you're trying to compare like user 1 to the next 499,000, and then 2 to the next 499,000, and like that's like not efficient, especially in a like sequential manner. So the ability to bucket and take 50 buckets at a time and then do them in parallel. Yeah, so obviously there's a pre-processing step there where you have to figure out what makes those 500,000 people similar, and like what's the like threshold for these people to be similar, like for these buckets. But at scale, you're always trying to reduce dimension. So sampling features, so like you have movies, like trying to figure out which features maybe can be combined or which ones can be reduced. Just to simplify shuffle across the network. And seek performance gains at like all layers, right? So disk and then also CPU. Something else that like Tungsten does is these data structures, right? They're like customized for sort and then shuffle type of workloads, right? So picture like your like classic TIM sort algorithm, right? Which is quick sort and a merge sort kind of thing, where it's not just one value anymore that you're sorting, it's key value pairs, right? So there's some tricks you can do there. There's pointers, obviously like using pointers, but we'll talk about it, like using pointers, but then also kind of pulling out part of the key so that you don't have to dereference that whole record just to look at the key. All right, so I sort of mentioned mechanical sympathy. The start of Tungsten actually was this 100 terabyte gray sort challenge, which was mentioned earlier, right? The whole goal there was, right, like you generate like 100 terabytes of data, just randomly generated data. You like pipe it into these systems that are built for short and shuffle, or like shuffle. So I think the last record was 2013, by Yahoo using MapReduce, right? And they did it in 72 minutes. Spark came along last year, end of last year, I think November, and did it in 23 minutes with like a tenth of the servers, right? And then also we'll talk a little bit about shuffle service and then like dynamic allocation that's sort of auto-scaling up and down. This term mechanical sympathy, there's a good blog. This kind of restates what I said. So the Daytona Gray sort focused on network and disk. Those are sort of like the low-hanging fruit. Like they knew that they had a lot to optimize there. So the whole point was to saturate the network and to saturate disk I/O, right? Like disk throughput. And then Tungsten was sort of like the next level. This happens to all of us. We get kind of bored, right, with like the normal stuff. So we're going to go write our own garbage collection. So then CPU cache locality is huge. So this is kind of what I was like mentioning here about the sort of naive way to sort would be like to have a pointer to the record, but now to actually and so the thing with the gray sort records that they generate is it's 10 byte keys and then 90 byte of the payload, just some value. But what you're sorting is the actual key, right? So for me to actually go in and like look at the actual key, I have to dereference this whole thing, put all 100 bytes into the CPU cache, L3, L2, L1. So that's obviously you're just sort of like randomly going along, just kind of sweeping through. and like destroying any hopes of cache locality. So this paper was published in '95. So like this whole gray sort thing comes from Jim Gray, right, the famous computer scientist. And this paper came along about alpha sort where you pull out the key. Right, so that's kind of cool. So now I don't have to dereference. But the problem here is 10 plus 4. That's, like 14. I got lost for a second there. So what you're trying to get to, obviously, is binary, right? 10, so 14 isn't binary. But the key, it's there for comparison, so that's cool. But I think we can do a little better, right? So, 10 plus 4 is 14. Let's pad it. Let's put 2 bytes of padding. It's kind of wasteful, right? Like, why would we do that? But it actually does quite a bit for performance, because with 14, you're going to prefetch, right, like a little bit extra, and then that's not good. We're just going to waste it. So here, we're going to be on those 8 byte alignments. And CPU cache, the L1 cache, for example, is 64 bytes. So that's not a lot of room. And then L2, I think, is 256 or something, and then it gets slower and slower, but bigger and bigger. So there's this other trick here too, where you can actually do a prefix. So take 4 of the 10 bytes, and then keep it with the 4-byte pointer. And so now we get kind of close, right? Because we're doing lexicographical sorting. I can't say that term very well. We can get close, and then so we would only dereference if there's a clash between those first 4 bytes, right? So it turns out that that's actually the winner. Not by much, but definitely compared to pointer. Twice as fast. It's a little bit faster there. So that's the route that these guys went for the gray sort. And this was something I sort of was thinking about when I was researching this. I was like, wow, this sounds a lot like this whole DCA thing, the whole direct cache access. So just real quick, just to kind of bring this down to what's happening, between Ethernet and then RAM or disk or whatever. So at some point, we have to contact the CPU to figure out where to route packets from that are coming off the network. And the naive way would be to take the entire payload or the first chunk and then run it through the CPU, right? But the CPU only needs the first few bytes or whatever to figure out where to route it. So that's exactly what they do. They actually pull out that key and then kind of pair it up, the pointer back to that data, and then that's all that has to go through the CPU. CPU cache lines. This is off my Mac. 64 bytes for a Core i7. So 256 for L2, 6 megs for L3. This is kind of comparing sequential. This is what we want, right? Versus random. This is dereferencing. Kind of dig into those later, and then just a quick overview, right? There's 4 cores. This is hyper-threading going on, right? 2 threads. They each share the instruction cache. That's the I cache, and then D is the data cache. And then they share, the L2, and then obviously L3. But the further away you go, right, the worse in terms of performance. So here's the matrix multiplication thing I was talking about. So this is the naive way, right? So just a quick refresher. Yes, I always like to put that top one up there because it scares me when I look at the slide. I'm always like, oh God, this is like college again. But just think you're going here times here, plus here times here, plus here times here, right? So this is happy because you can prefetch, right? Think of data coming in, to build this matrix. But here, for me to go from here to here, I have to clear out this part, which, I'm going to get back to you later, but I just don't need it right now. So basically thrashing the cache, right? So get 3, get 5. So what do we do here? Exactly. Transpose, right? So, flip it, and then get both of these guys go in the same direction. Obviously you have to change this algorithm, but the end result is. So let's see, I've actually got a demo. I think for time's sake, I'm just going to get right to the results. I'm using Perf. It's a pretty powerful tool, right? Have you guys used this? Kind of fun. if you know what you're looking for, it's fun. So this is a really good diagram. This is actually from this guy, Brendan Gregg. Yeah, he's an Australian guy. Actually works for Netflix now. I took his class about 2 or 3 years ago and told him I was from Netflix, and he was like, yeah, what's the company like? And then 6 months later, he worked at Netflix. So he basically moved from doing all Solaris-type stuff to all Linux. Yes, I was super happy when he did that because, I don't really know anyone that uses Solaris anymore. Yeah, I would read his blog posts. I'm like, that's great, but I can't run your tools or your extensions because I haven't seen Solaris since freshman year of college. But yeah, so he's actually doing all this on EC2, right? Because that's what Netflix uses. They use Ubuntu, I think, or yeah, maybe CentOS, but yeah, obviously more Linuxy than Solaris. So yeah, he's been filling in all of the gaps where we couldn't actually, right, like we didn't have insight into these things. So like you see CPU, you see memory, you see virtual memory. Yeah, get hooks into system calls into the network. Okay, these are super powerful things. The things that you want to look for, obviously, page faults, right, like prefetches. That's exactly what, right, like we're going to look at next for that matrix thing. Yeah, so there's the scary command up there. But really, like the thing, that big string, that big comma separated string, matches things that are in here, right? So L1, and like the upper right there. So yeah, comparing it, this was 72 times for the prefetch misses. So this is all that clearing going on, right? So this is the nice friendly guy, and this is, yeah, and then that ultimately led to like a 10x slowdown. Yeah, like another scary diagram here. Yeah, this again from Brendan Gregg. This is some like pretty cool profiling you can do. This is called a flame graph. Yeah, I didn't know about these until I took his class a couple of years ago. But what was cool on Solaris is that you could get like Java stack traces. And so that didn't exist until that didn't exist for the Linux world until Brendan came over to Netflix. And now you can actually see these stack traces. Yeah, so these, right, like plateaus are bad. This is where like the CPU is stalling, right, like waiting for I/O, waiting for a prefetch, waiting for something. So what you typically want are kind of spiky, just get in and out, right? Here it's kind of stalling along. So this is actually from a simple word count from Spark. And each time, as I look at it, like I just think of, yes, I just want to sit down and like analyze it. I just haven't had time. But yeah, this is like the next, yeah, so this is the kind of stuff that the Spark Tech Center is working on right now. Right, like trying to help out Databricks find these different stall points, right, like beyond just what you can kind of reason through from a software perspective. Yeah, so there's a couple scripts that Brendan wrote. What you do is put perf into record mode and then run a workload and then type it through this flame graph Perl script, and then it outputs this image. And like you can actually roll over and see the stack traces, or you can, really get the stack traces with the most stalling, that kind of thing. Yeah, so I think a couple people had mentioned this tonight. The whole point for these like sorting challenges is the throughput. So we've got 3 times the throughput. We got the Honda and the Porsche up there. That's kind of funny. Yeah, 2,100 nodes versus 200 nodes. And again, these were virtualized, so this is EC2, right? So I saw this bill. Actually, I was at Databricks when this was going on, and somehow I, was standing by the fax machine or something, right? Yeah, like there's faxes coming in with invoices from Amazon. But that was an expensive bill. Yeah, that was more than my whole salary for 1 month. And so they actually did, so I leave it off because it confuses people, but they actually did 1 petabyte, so 1,000 terabytes. And yeah, they got like the exact same throughput. So it kind of shows you the scalability. Yeah, that number 65,092 will come back. It's 206 nodes times 32 cores. This is the configuration. The first guy mentioned I'm maxing out 3 gigabyte per second for the disk I/O. And so network I/O, we saw iPerf was getting 9.5 within like Amazon. So we were placed into these placement groups, kind of optimized networking, a couple other optimizations that we were able to turn on. So 244 gigs of RAM. One thing to mention, too, is that, so with this challenge, they completely disabled the in-memory caching. Right? So typically people always talk about Spark, the reason it's fast, because it does everything in memory. So the whole point of this was to not try to use memory, but to actually push the limits of the disk and the network I/O. So this shows that even with the pseudo apples to apples comparison, factoring out memory, that the actual throughput, the way that the Spark execution engine works and pipelines and does various optimizations can be 3 times faster. The configuration that's happened about Spark 1.2. Yes, I talk about this because Spark 1.2 was only a year ago, but this really was the start of what they're calling Tungsten, right? It didn't have a fancy name, but a lot of these optimizations sort of paved the way for the memory and then the CPU stuff. So they actually, more sort of interesting tidbits about the configuration. They use JDK 1.7, right? So they used OpenJDK 1.7. They disabled all caching, compression, speculative execution, and shuffle spill. So they didn't want any shuffle spill happening. Forced everything to be node local, meaning if you can't push your code to a node that has the data on it, right, then just don't do it. Just wait till that particular task frees up. So they use 2x replication, which I found interesting, because especially given the node local thing, you would think they would have to bump up replication. But for this challenge, too, all time matters from the moment that the program starts to the moment that it ends. So that all factors into the overall throughput. So that comes in here because they chose to use range partitioning. So typically when you have these big data workloads, you want to spread things out, using hashing, hash partitioning, get things evenly spread across the network. That's not the case here because we're doing this primarily sorting use case, right? This is a sorting challenge. So to move data and keys that are similar onto the same partition, this is huge. This is this is kind of a no-brainer. So the way that they do that is they sampled all of the data. They took 79 sample points from each partition, each of the 28,000 partitions, and pulled it back to the driver, and then sorted it, and then chopped it up, and then broadcast it back out, right? That's how they decided the ranges per partition. So, but that whole process took 10 seconds. So that's 10 seconds off of your overall throughput. And not too bad, but. So something else to mention, too, is that they didn't just run it once and then, move on. They were obviously doing a lot of empirical testing. That's how they got to the 28,000 number. And this is something else, too. Do you guys know this, that typically what you want to do is saturate, so sort of provision for about 4 or 5 tasks per CPU that you have? So I find this a lot when I talk to different customers that they choose the same number of partitions as the number of CPUs because it sort of makes sense. Why would I want to over-provision? But, you want to keep these CPUs hot, number one. Also, too, about 4 to 5 is typically the empirical best. And, what's happening there is that slower nodes start to just kind of trickle away. I guess you would say tasks won't be allocated to them, right? So there's 200 virtualized nodes here. Some of these things, just based on probability, they're going to get bogged down with something. So what you want to do is factor that in. If you don't do that, then there's these stragglers, these kind of long-running stragglers, and then things get a little hairy. So you always want to kind of over-provision about 4 or 5 times. As part of Spark 1.2, they built this new shuffle manager. Some of the highlights here. So typically, what they wanted to do is use less OS resources. So, before there were a whole ton of network sockets being open between mappers, reducers. There was, what they wanted to do too was go back to the single seek, and then sequential scan kind of optimization. So on the mapper side, when data's coming in, it's pre-sorting it. It's using tim sort within memory, and then it's going to merge sort merge sort. So there's actually one physical file here on disk, and these reducers call in and seek once to those keys that it needs. Right, these are different partitions, the different colors. It can seek once, and it knows when it gets to the next key that that's no longer, and just bails out. So it's not randomly jumping around with this is called the hash-based shuffle, which is the original shuffle. So then also when these reducers pull these partitions, they know that they're pre-sorted, so they can do a very, very efficient merge sort. Right? So versus the old way, which could just be in any order. There was a new network module introduced. The key here was using NetI, using zero-copy ePoll. This is huge. So this is going from the network to the disk. There's no user space involved, right? There's no Linux user space, so there's no copying. That's why it's zero-copy. Because typically the way it was doing it before, Spark 1.2 was just sort of the naive way. You would pull data in. You would create big, huge buffers within your JVM. There's a whole ton of garbage collection going on. So all that stuff goes away with NetI and this ePoll. The NetI is asynchronous also, so keeping the CPUs hot, keeping things going. So NetI too, they also use direct buffers. This is off heap. So this is the first time that you see Spark using off heap. Because, I didn't mention this before, but each of those 206 EC2 nodes has 8 SSDs. I think they were 800 each, gigabytes. So if you have multiple disks like that, there's some optimizations you can do. You can turn on num connections per peer, which says, hey, yes, I know that I have enough physical disk here, enough throughput, so try to use all of it. And then I mentioned earlier about building custom algorithms and data structures for these types of workloads. So they rewrote timsort. Something that really isn't talked about much here, but was kind of a fun Databricks water cooler talk, was that when they rebuilt this timsort, between JDK 1.6 and JDK 1.7, the main sort method on arrays changed. It went from I think it was quicksort or merge sort to this timsort, which is kind of So timsort, just by its nature, takes advantage of runs, right? So this is very effective, especially when you're pre-sorting on the mapper and then getting things that are in sequential runs. So it's highly optimized for that. So by rewriting it, they basically normalized JDK 1.6 and JDK 1.7. So they weren't relying on the arrays method anymore. Also, they introduced key value pairs into this, so it's not like your high school sort where you're just sorting keys, but you're actually keeping key value pairs together. I've mixed in a little bit of Tungsten here. This sort data format, I think that's from Tungsten anyway. But what you'll start seeing is, so there's this kind of base trait or base interface called sort data format, and pass in any kind of arbitrary key value. And what you'll start seeing is that that's starting to trickle into MLlib, into GraphX, into other areas of the code base that want to take advantage of this shuffle, sort and shuffle. So the other thing too is that the first couple iterations of Spark, the first 10, I guess, used Java util map pretty heavily. So sort of naively using a data structure that is optimized for so things like inserts, like deletes, things that aren't happening with these workloads. So typically, picture the reducer, that one image from before where it's pulling from all these different mappers and just wants to keep adding values. Right? There's no update, there's no delete there. By building this append-only map, they're able to do, I think they're using, the open addressing hash, the quadratic probing. And so these data structures have really good memory locality because they don't have to handle the case of inserts and updates. So as was mentioned earlier, the reducer is maxed out at 1.1 gig per second, which is close to the theoretical max for 10 gig Ethernet. And then the mapper's got their full 3 gigabytes. So this is sort of an aggregate. This took me a few minutes to understand what was going on here, but this is an aggregate chart of all 206 nodes and the throughput. So you have to multiply by divide by the 1.1, and then you get 206 nodes. But, that's where that calculation comes from. A couple quick things here. Yes, obviously the larger that you can, the more memory that you can allocate to your buffers that are handling networking and specifically receiving, the less disk writing you have to do, right? Because you can build up these huge buffers and you're not spilling and writing. So you always want to. The problem is, people always think of Spark with the cache abilities and the ability to just dedicate a whole ton of memory to your actual data caches, but you're actually sacrificing the sort of internals of Spark, right? So things like these shuffle file buffers. Trying to find that right balance is pretty good. That's pretty tricky, but very effective. This is the only cost-based query planning stuff that's going on here for the physical plan. Is this auto broadcast? So this is like a map side join, right? This is where you broadcast out. If you're joining a big huge table with a small reference table like a state code or for my data set or genders. So I have 17 million ratings, but that's for I think 150,000 users. And so I've got 150,000 line table that I'm trying to join with this huge 17 million table. So that's where this broadcast join threshold comes into play. Something to keep in mind here is that this is an absolute number. So this is if my small table is below this particular number in megs, gigs, whatever. So, which is kind of tricky to know. So what you want to do is call this explain on your SQL or on DataFrame, call that explain with true. So always pass true there too, because you can see the sort of progression from logical to the physical. Okay, I have a chart here in a second about that. So then comes along Tungsten. Focus on CPU, focus on memory optimizations. I think I have a few more slides, and then we'll get to the fun one. So more data structures, more algorithms. But here, instead of focusing on the sort of obvious, key value pairs and things that help out, on disk mechanical sympathy, what they're trying to do is operate on byte buffers. So being able to pack I mentioned before about having 16 bytes versus 8 bytes, by using prefix and not padding. I forgot to highlight the fact that you can actually then store twice as much, right? So, which is where the extra little performance gain comes from, is that the ability to pack in twice as much data, but then occasionally have to dereference that last 6 bytes or whatever, pays off. So, so just trying to get more data going through and trying to reduce the amount of CPU. So CPU. And then provide a path to off heap. So why is CPU the bottleneck? Right? I mean, CPU is doing everything. I should probably move this up because I always start here and then go. But it's used for serialization, compression, hashing, the CPU is way more part of this workload than it should be, or than it really could be before Tungsten. So, yes, obviously also, they've already maxed out network and disk, so what's left? Right, like CPU is left. They already did the gray short optimizations for the shuffle. For the network phase. Right, and then more and more people are starting to use like predicate pushdowns deep into their actual file system, right? So with things like Parquet and Orc, right, like you can actually partition at like a file system level. So not just using databases for like partitioning, but actually pushing these things down in. So, right, like for example, the like Parquet data frame or like data source adapter for DataFrames supports pushdowns, right? Like Cassandra supports pushdowns as well. The whole like idea being don't pull in that data and then just throw it away. So we talked about the hash shuffle manager. We talked about the sort shuffle manager before. These are physically, if you look at the Spark code base, they're in packages called hash and sort. And then there's Tungsten, which is called unsafe, and it sounds scary. Yeah, it kind of is scary a little bit. Just like the amount of code, and then specifically tests, right? There's so many tests around this new Tungsten code, but so much code has to change for this because like traditional UDFs have to be rewritten. You have to make pretty much all of your shuffle, your sort, right, like all of your comparisons, right, like have the ability to read these serialized buffers without like incurring too much CPU. Yes, as you can imagine, they would do. They create. So real quick, this is kind of the classic Java. I have 4 bytes of Java. Like how many bytes is it actually in the JVM? It's 48 bytes because of all the object headers, that kind of stuff. So this is pretty, this is pretty obvious stuff. Let's create data structures where we can represent a string with 4, 5, 6 bytes, whatever. So this is the sort of main like data structure that's being carried forward from Tungsten on. It's this unsafe row, so you've got like a bit vector here of if I have 10 fields, figure out which ones are null. This is if the value, the actual value is smaller, I think, than 8 bytes, store the value here. If the value is larger, like a larger string, store an offset from here. So this is the variable length. Like we've all done this before. And then bytes to bytes map. It's kind of if you think of this as like the next evolution of the append-only map, but more serialized, where it's packing all these key values together, like knowing that they're not going to be updated. Or this is the unsafe. These are the ones used by Tungsten. There's been some concern recently because JDK 1.9 is deprecating this, but they've assured us that they're going to keep these, or at least that's what they tell us. So, this is for doing your own like synchronization. If you want to try to like tweak things out with your volatiles and like going to main memory, this is I don't know, some other stuff that is scary. But from a Tungsten standpoint, they need to get to an array from a particular offset. They want to allocate arrays. They want to do like memlocks, that kind of stuff, or like mallocs. And then these are super important because this is what's actually going to let you pull ints and put ints as a serialized byte buffer. So this, I sat down one day and thought this would only be about 30 or 40 classes. I was watching NFL football a few Sundays ago, and I started typing and copying and pasting. And about an hour and a half later, realized that I had copied 200 files. So, yes, all of these need to change. And there's a lot there. There's all of the like left semi-joins, all these. It's a finite set, but it's just a lot of code. So I'm not going to cover this whole thing, but these are the different areas of Tungsten, like data representations. That's the data structures, code gen. That's what so that's what has to happen to those 100 UDFs or 200 UDFs, like sum and average and all that. Right, like where they can actually operate. And Yeah, so not only can they operate on these serialized buffers, but they can also generate code that is going to be 8-byte aligned and super CPU, like hash line friendly, right? So what you'll see is there's a method, I think GenCode or CodeGen or something, that is on all these these new data structures and these new operators, these new aggregate functions, UDFs, or AFs, where it's actually generating Java source code and then piping it through this tool called Janino, Janino, which then generates the byte code. Yeah, all the great details are in 7075. The ability to join. Yeah, so you'll see this all over join code, right? This is this was my worst nightmare when I discovered it, because we've all done this where you put if statements in. If I'm in this mode, then do it this way. Right? Otherwise, do it the normal way. Unsafe shuffle manager. That's what there's. Hash, sort, and then there's unsafe. Memory sorter, external sorter. Here's more about CodeGen. The problem here is when you have polymorphic structures, right, like within, which is good, object-oriented programming. So you have base classes, base traits, you have different implementations. Everything is nice and clean from a compiler perspective. But from a JVM inlining, from a tuning perspective, these virtual function calls, right, from these polymorphic structures, destroy everything, because it literally just can't, doesn't know what needs to be inlined. So this is where code generation comes in. It's basically tricking the JVM, right, into thinking that it's a solo class, right, that there's no polymorphic behavior here. Also, too, boxing. This is kind of the JVM developer's worst nightmare, runtime developer, in terms of performance. If you're going between primitives and objects, you're just destroying performance. If you want to look more into this, there's this technology, or a set of macros called quasi-quotes within Scala, kind of the pattern used here, where you can actually manipulate the syntax tree, like a Scala syntax tree, and then do all kinds of rewriting. This is how you would push filters up and down. This is what Catalyst. Yeah, you guys might have heard of Catalyst. That's the optimizer used by Spark. So now, Catalyst was the replacement for Shark, right? So for Hive. So Shark used Hive underneath the covers, the Hive optimizer. And Hive, being MapReduce based, doesn't really play nice with the way that Spark does things. So, they made a pretty firm decision a couple of years ago to start writing Catalyst. So this would be, if you actually wrote the code yourself in CodeGen, very similar, or thinking about 8-byte alignment and cache friendliness, and then if it has to be polymorphic and all the slowness of the virtual function calls, and so 4 or 5 times different. This doesn't look that good, but here's some of the UDFs that. So physically, there's this huge umbrella Jira, and they just beg the community to please come in and take care of this. So you'll see so many pull requests and so many, there's tons of tests and everything, but just to do not, there you have to generate code and you have to understand quasi quotes and understand what's going on and write a million tests for it. So I think they got about 100 in for Spark 1.5, and they're just going to keep on cranking, right? So before Tungsten and before CodeGen, there was always this fear of using Hive UDFs, because before Catalyst didn't know what to do with these things. It couldn't optimize them. It couldn't rewrite them, and it didn't have it was just a black box to Catalyst. So we saw this quite a bit at Databricks, where customers came to us and they're like, we're doing everything right. We don't know what we're doing. And then the first thing we just got used to it was there's some crazy UDF that Catalyst won't know about. So this is the hook basically to start to get past that limitation. Okay, so I don't think I'm going to go into Catalyst, but you guys can look at it on your own. I think we're going to get to. Get right to the last section. This is the fun one. So, featurizing Spark ML. This is kind of a little hidden Spark secret, but things are starting to move to Spark.ml, org Apache Spark.ml. Before, everything was packaged under MLlib. It's not really a well-known thing. I probably shouldn't be touting it too much, but because I'm probably too close to Databricks and those guys. But what you'll start seeing is people are slowly rewriting algorithms that were in MLlib and pulling them into ML. And part of that is a focus on pipelines and sort of snapping into like scikit-learn and like the way that like a lot of these current like Python ways of doing things and just sort of the terminology. Because remember, MLlib, right, so that came out of a lab, right, like the Berkeley Amp Lab, and wasn't right, like yes, they knew about the industry things, but it just wasn't like a first-class citizen. So there's partially that, and then partially this Tungsten stuff. So right, there's a lot of work going into making MLlib streaming. For example, Spark 1.6 is going to have Tungsten support, so like a lot of things going on beneath the covers there will be byte buffers. Spark SQL is obviously kind of the forefront of Tungsten right now. Let's talk. Right, like how much do you guys? Yes, I know you're like a machine learning expert over there, but yeah, I mean, who's used these algorithms? Who's used like matrix factorization? Yeah, anything you guys use these? Good, then I get to sound super smart, even though it's not really. So if you guys have the energy, if you want to go to sparkafterdark.com, and yeah, help me out here, because otherwise this is going to be kind of lame. But go to sparkafterdark.com, like on your iPhone, anything. There's absolutely nothing being tracked here. This is totally anonymous. I'm in Europe, after all, right? Yeah, I think I've been here since they moved over, right? So this new, did that policy just go into place? Because all of a sudden, every site I'm on, like when I go to Google, it's asking for permission to have all my information. I'm like, I don't remember this happening. But sparkafterdark.com, this is this really simple UI. I realize these are all American actors and actresses, but if you just pick three, where that came from. You just pick 2 or 3 here from each section. Hopefully, okay. I don't know what happened here. What we're going to do is actually generate recommendations live, specific to this group. Okay. Is Zeppelin, and this is totally open to the public. And in fact, I even have a warning that I put up, please do not modify anything because I'm doing a demo. You know, I was at the Cassandra Summit a couple of months ago, and yeah, there's some hackers in that Cassandra community because they were in there just tearing me apart. Like, no security. I'm like, guys, come on, I'm trying to help you out, you know. So we'll do a quick. This is the reference data. So let's assume that you guys clicked around in there some fashion. Yeah, I mean, I chose Zeppelin versus IPython. Like, yeah, I literally cannot get IPython or like Jupyter working on my machine. I have no idea what I was doing wrong. I really wanted it to work, especially because the IBM, like Bluemix uses it, but wait, what's that? In the cloud, yeah. Yeah, that's true. This is very true. Okay, so this is the DataFrame API. This is the new one. It's gone through 2 or 3 iterations. And yeah, I know that's because of the book. So there, you do read and then you do format. Here, passing in some nice people over at DataStax, the guys behind Cassandra, have written this for me. It's super optimized. It knows which nodes to go to. It's pushing things down. It's doing everything it can to help me out. Passing in the Cassandra config, which is the key space, and basically database, table, that kind of stuff. And let's see, these windows get all tiny and stuff when switch resolutions. Let's see, there were 6 people. Ooh, all right, we got 80. Thank you. So these are kind of like ratings, but it's like, these are just likes. So picture just a 1, would be the rating, which more matches Tinder, right? You just swipe left and right. Yes, I like them. No, I don't like them. Which is horrible. Let's see how many distinct people were in here doing this. 15. Cool. Actually, I was 1, so 14 others. Let's register a little temp table action here. Do you guys know why people do these temp tables? Anyone have a guess? I don't know either, actually, why they do it anymore. Because DataFrames can do everything. But the one thing that it can do is you can quickly bust out into SQL. And so you could do, but with DataFrames, you can also do .SQL and then do the exact same thing. So now you have to remember that you have a temp table, and you're not quite sure how the temp tables work. Who's it competing with? I don't know. But temp tables were all the rage about 6 months ago, so I'm sticking with them. Let's see what we picked here. Who do you think's the guest? It's always Leonardo DiCaprio. Always. Oh, Morgan Freeman. All right. Go Morgan. James Franco. Yes, Anthony Hopkins was big up in Scotland area. That was the only person that they recognized. One thing, speaking of the DataFrame thing, so this is an example, like I said, of doing. So I'm just, giving it SQL context, and I'm passing in the SQL, and I'm getting back a data frame. All right. Well, is that the same data frame as if I just did a pure. So this is the exact same query. I might be able to get them both in focus here. This is the exact same query, but doing it for data frame way. I'm doing group by. I'm counting. Even giving it the same alias, sorting, same exact thing. What is important to show is that this is the exact same physical plan, even down to the names of things and stuff. So, these plans got a lot more difficult to reason through after Tungsten, because everything is now Tungsten this and unsafe that, and it's basically going back and forth between byte buffers. But before it was nice and easy. You'd see filter and things kind of made sense. But what you want to watch out for here is if you are doing joins, right, this is how you would find out if you're getting that auto broadcast thing happening, that map side join. Because a lot of times we would see this, and people underestimated how big their table was. Once it got pulled into Spark, on disk it's one size, but once it gets pulled into Spark, blown up into huge Java objects, now it's past that threshold that they set. But that's absolute value. Okay. So now we're actually going to run this in whole, run all paragraphs. I'm going to add in a little reference data, more than was there before. So before I was just, kind of pulling in, I think, their names just for the bar chart. But here, I actually want the image, because now what I'm going to do is sort of follow that big thing and go back to Elasticsearch, and now we're going to be able to, from the UI, query it. So hopefully that happens. Let's go back here. There's a big please wait, so that I know. So typically you wouldn't have the data scientists, you wouldn't have Zeppelin part of this workflow, but I'm doing it. Typically, you'd have another streaming job that would be aggregating, that would be building models, in the background. One comment on that, since we're not going to go into the full streaming section, is the best recommendation for streaming is get stuff out of streaming as quickly as possible. Don't get too crazy in streaming. Everyone wants to, populate Redis and populate Cassandra and build a model and that might work for, lower ingestion rates. But once you push that thing out, into production, what's going to happen very quickly is that processing time is going to start to get larger and larger than your actual batch interval window, right? So, typical batch interval windows that we see, I've seen them as low as 500 milliseconds. People try to go below that, and if there's one GC pause, you blow through that. So the new Spark streaming as of 1.5 has back pressure support, where you can actually, stop pulling from Kafka, or kind of throttle things a little bit. But that only works with things like Kinesis and like Kafka, right? Or I think Flume is going to have that support pretty soon too, or Spark is going to support Flume with the back pressure. Just uses typical control theory stuff. This company TypeSafe, the guys behind Scala, Martin Odersky, those guys, they actually contributed that about 2 or 3 months ago for Spark 1.5. So we'll do another one here real quick. Do some PageRank action, since everyone loves PageRank. Fairly easy to reason through. Right, the way I always describe it, which probably isn't the right way, but if you have $1 and you can give it out to 10 people on this dating site, or pick 10 actresses or 10 actors, right? Like, you really want to be scarce about it, and then people at the same time are also giving you dollars because you're a good-looking fellow, good-looking lad, whatever. So at like the end of all this iterating, like, you're going to be left with some amount of francs. Is it around it? Francs? Yeah. Which, I still haven't converted. I'm still rolling on euros as long as I can. So we did that. This is now the right side of things. I didn't show this before on the top K, but this is like DataFrames. I'm writing, passing the Elasticsearch. Someone over at Elastic has written that for me. They tuned it. So there's different save modes. There's error. Like the most interesting one is error if there's already data there for this particular key. So it'll error out. So I'm basically using Elasticsearch here. I'm taking that like unique ID that's at the top of your Spark After Dark, just like a 6-digit thing, and I'm like using that as a key and stuffing it in. So I'm basically pre-generating these things, and then when you click the button, it's going to search for that user ID, the anonymous user ID, and it's going to get the top influencers, right? So things like, like LinkedIn, right, would use top influencers. People, like Twitter uses this for, obviously Google. Yes, I clicked the link twice. That's why it shows up twice. My UI skills aren't very clean. Let's do a quick matrix factorization, ALS. Just want to mention the intuition here behind this, which I think most people get. That's not good. It's going to come to an end pretty quickly here. But think of, so before I showed this sort of overall light graph, for the PageRank example. Now let's go back to sort of like whole like Netflix way of thinking things. User items, where here items are people, there's actors, actresses, and then this is all of us. This is all like 15 of us. Stops right there. So we've selected people, but there's a whole bunch of like sparsity there, right? So if we can take a snapshot of that and factor it out, I have to change this. I was trying to show why it's called alternating least squares, but I didn't do a very good job. It basically holds this up. So, right, like what's happening here is that we want to factor out 2 smaller matrices that, when multiplied together, give me that snapshot. And so the thinking here is that these values aren't going to be zeros and ones that I fill in, but they'll be 0.1, like, right, so they'll be so I can actually sort it. So say that I'm user number 5, 6. As I log in, I'm going to sort this to figure out who are the highest ranked people for me at that given point in time. This is what like Netflix does. This is what like Amazon does. Typical user to item similarity type stuff. And like the whole alternating part of it, like the reason it's called alternating least squares matrix factorization, is the way that this is implemented is it's going to hold one of these fixed and then calculate the other, hold that one fixed, calculate the other, and just keep going back and forth until some sort of convergence, right? Until things don't change below a certain threshold, for example. Let's see, I'm going to write that out, same way I did before. I get something here. I'm not getting anything. Did that work? Oh, I don't think I ran it. Yeah. There isn't much more after this, but anyway, so yeah, you would see the. Looks like it didn't run. This is the famous notebook bug. Yeah, so any notebook, yes, even Databricks Cloud, or it's just called Databricks now. Yeah, so they have it's like notebook product that looks a lot like IPython, like a lot like Zeppelin. In like reality, it's a pure rewrite. It's neither of them, but yes, even they have this problem, right? So any notebook, what you're doing is each cell, right? Like when you run it, it's creating this sort of tiny little class, right? This like namespace class, and it's like you'll see the errors like when they pop out every now and then, where it's like percent, something percent, something percent, something percent, and it's sort of like it's like the notebook, and then the cell, and then anything going on that's needed by that cell, it's sort of namespaced. And the more and more that you run the same notebook, the deeper and deeper that gets. And yeah, you literally run into like the JVM. It's just too long of a class name. So kind of silly, but that's what's going on there. I was doing a little too much testing beforehand. All right, real quick before we lose battery. Mr. Romeo, do you know what happened here? Did I? Yeah. Just trying to get back to the slide share. Let's pull it up. Yeah, it's fine. I'll find it again. Yeah. I think we're about. So that was the live demo. That was that entire thing that we went through. Now full screen, sure. Types of similarity. Yeah, you guys have probably all heard about Euclidean cosine. Right, like Euclidean is kind of as the crow flies. The problem here is that you've got magnitude. So these two people are actually more similar than what the like vector space shows, right? Like this is on a like 10 scale. That's on a 1 scale, kind of a silly example. What you do is factor that magnitude out by using cosine, right? So taking a look at angles, and then yeah, this is what was kind of like loosely called the Shawshank Redemption problem at Netflix. The first day that you started, everyone had to say what your favorite movie was, and it was like probably 80% people would say Shawshank Redemption. I mean, it was like totally skewed. I think it's the first like movie that people remember thinking like, oh, like this is a cool, like I should tell other people that I think this is a cool movie, and then yeah, they'll think I'm cool. Yeah, I don't know, or like maybe that's just what I did. But what you want to do is factor out these popular people. So I was kind of going back to the dating example here, and kind of like Matei is the main creator of Spark, I guess. Yeah, he's a pretty popular guy amongst the ladies, right? Like not going to lie, especially conferences. Right? Like a lot of like Romanian girls come up to him a lot, and they speak Romanian and have a good time. And I'm trying to figure out if they have a question. They don't want to talk to me. They just want to talk to Matei. And so by factoring him out, now we're surfacing up more high value things, right? So for Netflix to keep showing Shawshank Redemption is not really that high value, right? And they have to pay for Shawshank Redemption, right? So trying to get Matei to come out to an event that's not like a speaking event just wouldn't happen. But I can get sort of lesser popular things that are like just as appealing to people. And so yeah, this is how Netflix keeps the costs relatively down. Like something else Netflix does, obviously they know everything that you're doing. They know where you're scrolling. They know which are like movies that you're like reading about, which ones you've dropped off early. Some of the obvious stuff, they know your search terms, so they can use all that. It's sort of like gambling with all the odds in your favor. Like they have all the data, so they know when they come out with these like original TV shows, like they know what you're going to want to watch, so they can pick the shows that they invest in. So, so like the name of that like technique is this is like log likelihood. So kind of bounding and start de-emphasizing these popular outliers. So yeah, when you're trying to find similarity, yeah, I mentioned this earlier, you kind of have to compare everything to everything. This obviously doesn't scale very well. So there's ways to approximate. You can do sampling bucketing to get rid of M, so that's your rows, and then N is your columns. Things like principal component analysis help out with that. They're not fully like equipped. You kind of have to know what you're doing, but it helps you with the whole dimension reduction, which is one of the themes that we mentioned earlier. So a little bit about, there's this pretty cool algorithm. Twitter uses this pretty heavily, called DIMSUM, Dimension Independent Matrix Square Easy MapReduce. So this was a MapReduce particular workload. So yeah, they were looking at like how much HDFS bytes were being written, and yeah, they got 40% gain. What they were trying to do is find like the ability to serve up similar ads to people. So not necessarily in like real time, figuring that out, but sort of pre-calculating it and finding ads that are similar, so that when you are in there actually poking around Twitter, that you'll be served up similar. Now, this is one of the coolest things. This would come up almost every week at Databricks. Pretty much all of our customers, once they got past the initial just trying to get their data into the product, into their notebook or onto S3, they would, which is what Databricks is like used pretty much. It's all Amazon based. But yeah, this is what you would do. You would pre-process based on some kind of similarity hash function, and then bucket these things. So the cool thing here is that you can actually then process similarity within the buckets in parallel. So just doing 50 buckets, the way that the Big O works out, like you're saving 4 orders, right? So that shuffle, that's all the bad stuff that happens here. But yeah, we would see this a lot. People had like 500,000 M, and they had a huge amount of features that they were trying to find similarities with. Like features being like things that they clicked on and topics and other people that they follow, stuff like that. So, there's this algorithm called Spark-Hash. This is off Spark-Projects, so Spark-Projects is just kind of a metadata, fancy-looking site that just points to these GitHub projects. So people that have built their own algorithms. So this actually is from this pretty famous book, Mining Massive Data Sets. And yeah, and I think Spark 1.6, they're actually going to have a first-class locality-sensitive hashing algorithm that I think is similar to that, but I haven't seen it yet. Pretty classic if you have a bunch of like a sparse matrix or a bunch of frequent values, you can factor them out. So yeah, that's why you see the Spark code base has dense matrix and sparse matrix. These are physically separate code paths because they do things differently. They store the data differently. Different algorithms work better on dense than sparse, that kind of thing. One thing to mention too, this kind of reminds me about like the most frequent value being 0 or being, it doesn't necessarily have to be 0. This could be 999. What we saw, more than I thought we would see when I joined, was people would start to see a lot of skew. So back to the hash partitioning, when you're hashing a key and then sending it to the same node, right? The same partition. What would happen is their stuff would be working fine, and then one day they'd be seeing a whole ton of data ending up on one node, and of course that's skew. And you start to look at it, and it's the same partitioner that they're using. They haven't changed any code in a while, but what they forget to tell us is that upstream, one of the application teams did do a deploy, and you could trace it back to almost that exact day. And what would happen is that the application would actually have a bug in it where they would be logging 0 for the person's user ID or for whatever was being used for the key. So keep an eye on that, because this has come up this actually just came up within IBM the other day. Also, is that it was just bad data. I'm still going on. Okay, that might be the end of that. I've got my charger. Yes. Any questions? Well, I think I have a couple more slides. It might be interesting. Is it useful? impressed that you guys have the. Love it. Yes, I had to go out and buy the Mac version of this thing just so I can get it to somewhat stay in other countries, but typically like that big honking thing sits in there and just falls down. Like, this is genius. Love Zurich. The fateful Mac issue. Crap. Yeah, this happens from time to where it goes into like old school Atari graphics mode. But I think we're back. Where it's like blocky. Yeah, have you guys ever seen that? Like, does it do that when you run out of battery? Is it just? I mean, it's a year old. I don't know why. Okay. Oh no. Yeah, so do you guys have any questions? Yeah. Oh. Yeah, like to actually generate the data and to simulate that. Yeah. Yeah, because what's interesting is now that Tungsten has come out, I mean, I'm sure within the next couple of weeks we're going to see something out of Databricks. Right? Like we're actually trying to do it as well to benchmark with the same data. So for the gray sort, they actually use this tool called GenSort, and that's fully available. That actually is part of my VM or my Docker image. So. And then from that point, I mean, I would start with the optimizations that are like very well known about the like Daytona stuff, like even some of the non-intuitive stuff like disabling spill and like disabling compression and that kind of stuff. But like again, the whole intuition there is that they don't want the CPU involved, right? So that's why they were disabling like compression. But yeah, it's like fairly easy to get up and running. You would, that code. Yes, I don't think Databricks has actually like released the code that they use for the challenge. Right? Really? Yeah. But yeah, you have the 10 bytes and then you have the 90 byte payload. And, because that. Oh yeah, sorry. Yeah. So the question here is the sort of overall questions are, how do you like benchmark this like next round of like Tungsten type stuff? Is that kind of like what you're getting at? Yeah. So like what would I want to do now to compare like the actual engine itself? Yeah. So that's a good point because the new goals now are well, I mean, I guess you're still trying to optimize throughput, right? And like you'll still see like pretty because with the serialized buffers now, you'll be able to keep everything serialized throughout the entire pipeline, right? Yes, in memory and then on disk and then like through the network. So, I mean, I would use that same data set for sure, right? And then keep an eye on some of these things like the sort data format, that bytes to bytes map, right? And if you can somehow like instrument those things and I mean, like the way I'm doing it, I'm trying to kind of leapfrog it and go this flame graph route, right? And like really, really use perf pretty heavily because I don't think that was being done the first time. I think it was just let's just start the wall clock and then like divide and figure out how much throughput we had, right? So, but for like this kind of stuff, to actually go in and then disable Tungsten because that's just one key, right? That's just one configuration, say like Tungsten equals false, and then all of those branches, if I'm in Tungsten, all that stuff, start going the old way. So. Yeah, like that's one way to do it. Just fire up perf and see what's going on there. I mean, obviously wall clock is going to be the ultimate. what were you thinking? Yeah, I mean, do you have any thoughts on that? Yeah. Yeah. So, I mean, just for the remote audiences, trying to figure out. So you're setting up the cluster, and so is there something specifically that you're trying to is there a particular workload, or is it just here's my configuration, I'm trying to compare? Yeah. Because I mean, then people start asking about things like tachyon. Can I do that off heap? Is it? And I'm particularly interested in turning on the actual off heap flag, because that's not on by default, right? So I'm curious to see what's going to happen there. And I mean, my gut feeling, and I don't know those at all, but is that was not the priority for Tungsten, just given time. I mean, what's crazy about Databricks and the whole Spark, the way things change within Spark is they'll come up with an idea, and then 2 weeks later they've got this thing all built out, right? And then they have a community that's coming in, and everyone wants to be a contributor, committer, so everyone piles on. But okay. Yeah, I mean, that's going to be one of my big focuses when I get back from my dream vacation here in Europe. Okay, I think I just have a couple slides on terminology and that kind of stuff, so probably get through here pretty quickly. Parquet. Yeah, there's some benefits. There's a lot of work being done on putting, this is turning how you would typically store data, in a logical or a database row-wise, flipping it over and doing everything, column-wise like this. But the ability to put a min-max sort of thing, so picture this being, if this was all the same column, not necessarily ABC, but if it was all one, you could actually skip over whole files because you know what the range is, so you can just inspect the very first couple bytes of that file and then jump over. So that's probably assuming that you're not partitioning or this is within a particular partition even, so you could skip over. The other thing about Parquet, I think that's the next slide, is the compression. So the fact that you are storing all these columns together is huge because you know that they're all the same type, right? So you're not jumping from name, string, to age, numeric, that kind of thing. So there's a whole ton of bit packing, and if it's data that is categorical, if there's 23 football teams or whatever, 50 football teams, you can do dictionary encoding and all that kind of normal stuff. Oh, that's actually from a different. I just happened to jump to this, which is not part of the actual ML talk, but this is a new feature here. I think this came in 1.5, where you can actually view the query plan, right? So Spark 1.4, you can visualize the DAG, right? The RTD DAG that's being built up. But this is cool because it shows you, if you're applying filters, how effective are those filters, right? This is how many rows came in, this is how many went out. Here's your broadcast hash join. You always want to keep an eye on that. Things like limits being applied. This convert to unsafe. This is the byte arrays. Tungsten project. So it's a particular kind of project where keeping everything serialized. So that was just a random click there. So cold start problem, if you guys aren't familiar with this, it's Netflix has this, pretty much everyone with a recommendation has this, where new people join, you don't know anything about them. That's where you fall back to some of your non-personalized recommendations, or you present them with what kind of movies do you like, what what types of actresses do you like, that kind of thing. Yeah, we talked a little bit about the feedback. So, like when I first joined Netflix, they were pretty much all about the explicit feedback, which is ratings, right? Like the 5-star ratings. And then as your M starts to grow, right? Like I think my first week, that next weekend was the, I think, 20 million party, like where they rented out this place called Treasure Island within San Francisco. It was totally crazy. They bought hotel rooms for everyone. And, yeah, I got hammered. I didn't know anyone, right? So I'm going to get drunk and make a fool of myself. I still made it 2 years, though. So, yeah, nothing. But then, yeah, so as, N starts to grow and you aren't able, people just aren't rating, right? Like maybe 1% rating kind of thing. They had to switch over to the, like what's called, like the implicit feedback, which is more like behavior-driven. So what you'll see in the Spark code base, there's actually 2 different code paths for doing recommendations for explicit and then for the implicit. And it's the way that things are being weighted. These like ratings themselves are very, very high value. And then, but the implicit stuff is more. There's just so much more data, but not necessarily strong signals. Feature engineering, trying to do dimension reduction, trying to figure out which dimensions, which features are the most significant. Yeah, don't forget, like combining features could be significant. So things like principal component or like analysis don't give you the exact component, like the features themselves, but they do tell you that there's 5 features or 10 features within this feature space that are significant, and yeah, now it's your job to find them, right? But it could be any combination of those raw features. Things like, so every model pretty much has its own parameters. So these are called hyperparameters. And yeah, I mentioned, I think, a couple times for PageRank and then for matrix factorization where you get to a certain threshold where things aren't changing as it's alternating, holding one fixed, going the other way, or as the frames are moving around. Yeah, I'm getting better. And so what you need at some point is some like sort of threshold that once you like go below that's going to trigger it. Or for like things like decision trees where you're trying to build up a model. How deep are your trees? Things like that. So there's ways to actually build a grid search. This is like the most common thing. It's totally brute force, but it's very, very highly parallelizable, right? Where you can do, every combination of every feature, model parameter, and figure out like what's the best combination. So those are kind of fun ones to tinker with when you're starting to learn MLlib. This idea of k-folds, this comes into play when you have a very limited amount of data, and you're trying to get the most value out of that small amount of data. What you do is chop up like the actual model training data into k segments, and then change the role. So you would train with the first 9, and then you would test with the 10th, and then you would train with the first, and then 3rd through 10th or 9th, and then or 10th. Sort of alternate the roles, and and then pipelines. Those are kind of the new hip thing now for ML. A big trend that's happening this started with 1.5 and it's continuing on with 1.6. So again, this whole trend of coming out of the lab and then realizing that there's other like algorithms that are useful that people use on a daily basis. And at first, Spark was very against taking in any new machine learning algorithms or like graph algorithms that were not parallelizable, were not distributed, right? It was kind of a hard like nose thing, and because really, I mean, it's just like you're not going to get much better performance than you would on your local laptop, right? But then they realized that Spark, everyone wants to use Spark, everyone's using it for everything anyway, but they have to keep going back to their local laptop and to RStudio and things just to do single node algorithms. So they're getting more and more hip to this. also too, they're starting to add heuristics. Yeah, this is something system, like the IBM system, like ML stuff does, like pretty well for its optimizer. Is it can like basically, like determine at what point, like does it make sense to do things locally versus distributed out. Right? There's got to be some threshold where, so Spark is starting to do that. They're like talking to us about system ML and about how what our like threshold like properties are and that kind of stuff. So that way it's just one algorithm, but if like for example, PageRank, which is parallelizable, if we can pull that out and just do it locally for some small set of data. There's this new package called PD Spark that's starting to come out. So it's got scikit-learn integration, R integration, that kind of thing. We'll start seeing more and more of that. I actually don't know too much about that. That came up at the summit last week. I haven't gotten too much chance to look into it. So yeah, we did these. Did that. Oh, yeah, these are the last few slides. So yeah, just to kind of wrap it up here, like some of the fun stuff. Yes, I noticed that people in like me also, I really like text processing, textual type of like machine learning because I can relate to it. I can, it's human grokkable. But like the ability to, recognize entities like Sonicare, that's a type of like electronic toothbrush. Cubs, my Chicago Cubs and cards are not the same. Let's avoid those, even though from a Levenstein edit distance, they're very similar. Also things like this, like music and country. This is actually my profile, by the way. Like music and country. Yeah, I'm a big fan. So this person is also, but not unless you had a K-skip, right? Like a one skip in here where I'm saying, it's okay if the words aren't right next to each other, but maybe one away, two away. Right. So obviously, like that's going to increase the training time and the time to find similarity. But finding that's pretty high value. Right? I pretty much cover all the bases. I realize I've got hip hop and everything, so that no partner will ever slip away from me. But so that would be finding people like surfacing profiles I have not yet seen that have a lot of similar keywords. And now this is actually even more higher value. This next one, it's the same thing. I should probably change it because it's too similar. But this is, so let's take, this would be better if I didn't have my own. But let's take someone I've already picked, right? Like someone that's already been surfaced, I picked them, and now go through and find similar people I haven't seen. Right, so take mine out there and take the other 12 people that are part of Spark After Dark, or 14 people, and we'll, then we can start to surface that up. This actually happened to me recently, and I couldn't figure out why, but this person sent me an email, and their email rose to the top, and it was flagged, and it was like, this person loves you, like you must contact them immediately, kind of thing, and so. I contacted, and I didn't hear back. But what was interesting is that like there were a lot of similarities, and I could tell that. I mean, just sort of like from an intuition standpoint, I could tell that this person put a lot of effort in, like actually read my profile, right? Because they actually did comment on the toothbrush and maybe California. I mentioned West Coast, that kind of stuff. So. Skip the demo. I'm basically using TF-IDF, Word2Vec to take profiles like this or like emails, pull out the keywords, the most valuable words, get rid of stop words, have and all the normal stuff like that. This is typically so Spark has an adapter for the Stanford core NLP, right, like library, that basically just adapts Scala to Java. But that's kind of the first time that you start seeing some of these algorithms like sneaking in to Spark. Sort of, that one's actually on Spark packages, and it's just an adapter, but you still need to pull in Stanford core NLP. It just happens to be written in Java and also compatible with Scala. Yeah, this was kind of fun. This came out of a blog post when I was putting together this presentation. Someone forwarded this to me. This guy out of Vancouver, Canada. Kind of back, I was hoping that the guy from the first talk was here. But like the ability, as I'm swiping along in the background, this could be like assuming the people's images are all, the same way, or the program can scope it down that way, to find to find a pattern in, the way I'm swiping, right? So I think like studies have shown, these like elusive studies have shown that about 150, 160 you can actually build what's called an eigenface, sort of like colloquially. That's an average of the people's, so certain features that would stand out are distance between the eyes and mouth structure and, facial structure, that kind of thing. So like this guy actually built a dashboard, and he reverse engineered Tinder and the REST API or whatever, and was able to sort of overnight just sift through thousands of pictures, and woke up in the morning and he had people that he was attracted to, or that were similar to people that he had previously swiped. So saves him. He's a really good-looking guy too. So it would save me like zero time, but it saves him a lot of time. This was the other goofy thing. He built this conversation bot, like a natural language processing conversation bot, where, again, he had part of his he had this huge dashboard. He doesn't maintain it anymore because he got slammed so much. Like everyone was trying to submit pull requests and add features and everything. He just got tired of it. But just kind of throw out a few generic lines and see how far people get. Have canned responses. How was your weekend? What are you doing this weekend? And run a little sentiment analysis. Pretty straightforward. Figure out if it's positive response, negative response. This one's kind of cool. This is one I've actually been working on personally, just because I think it's a fun media. I still have a love of movies and like music and that kind of stuff. So the ability to sit down and choose, if your wife, girlfriend wants to watch that, if spouse wants to watch that, and find things that are sort of in between, right, based on similarity. So this is item-to-item similarity, and then also using shortest path, right? So picture edges between these movies, and the edge has a number, and that's how similar these movies are, possibly along different features. So message in a bottle, similar actors. Surprisingly, and I didn't realize this until I was researching, I was trying to get Waterworld in there somehow. That was my main goal, and I just fanned out from there. And it was actually pretty obvious, but Mad Max and Waterworld have very similar plots. So typically, there'd be 10 or 12 of these, and I've seen people actually pull in movies and books, and you can kind of reason through. That's another reason why media kind of stands out with me, media and text processing, because you can sort of reason through it a little bit. And then the final recommendation, kind of goofy, but finally get off your computer and just meet people, right? So, someday I'll do that. Here's some relevant links. This got longer and longer as I went through. This is Brendan Gray. You want to check him out. Watch his blog. Anything, and everything that you ever wanted to know about CPU caches, a lot of those images that I stole are from those two links there. The other, of course, Databricks blog is all over this. The Netflix blog, techblog.netflix. If you guys want to pull this down, I think third or fourth link there is the GitHub and the Docker Hub. Things I'll be working on next, obviously some of the tuning stuff, but some of the more tangible things. I'm trying to auto-scale Spark, right? I mean, this is huge. It's a fairly tricky problem, but Docker is starting to come a long way with the networking and Docker Compose, and there's a couple other things that are helping stuff out. So building out more Zeppelin notebooks. I'm also going to add, of course, more Jupyter as soon as I can get it installed, or switch over to Bluemix. Do some more advanced streaming use cases. So, and I've got some of these already, but didn't show them, where I'm doing approximations. So, right, like Twitter needs this quite a bit because they have huge ingestion, right? They're just taking in so many tweets, so many likes, all that kind of stuff, that to use a typical Java hash map is just crazy, right? Because you would, right, yeah. So not only are you sort of, right, like using the wrong data structure, something that where things, yeah. I mean, basically, it's back to right, like an append-only type of right, like data structure, but like the ability to not necessarily keep the exact count. That's not really important, but maybe just sort of a relative count. So there's things like hyperloglog, count min sketch, this whole family of sketch algorithms they're called, that do some fun tricks with hashing and can, with fixed memory. So for example, I think hyperloglog or count min sketch, 1.5K can store 10 to the 9 counters, right? So I mean, this is huge, right? So before they had to have huge, JVMs or huge, right, like Python processes and that kind of stuff, PHP processes out there that are holding all these big fat maps. But yeah, now and I think it's 2% error, that 1.5. Oh yeah, and then the tuning stuff. Let me engineer this if you like following me. Yeah, please don't follow me. That's creepy. If there's anything, here's an example of the DataFrame explain true. So this is the old, pre-Tungsten days where everything was kind of fun and easy to read, but you see, logically, you've applied two filters. So yeah, I made reference to that gender data set. Has like actually 3 genders. It's got male, female, and then undeclared, undecided, something like that. And so I'm trying to factor out male and female and just focus on the use. So I'm giving it 2 filters. Like the logical plan sees 2 filters. I start to analyze it. I start to collapse these things. This is where you see the optimized plan. Yes, each of these would be one pass through the data, right? That's not good. So here, because of the way that the filters are and some of the right, like optimizations being made by Catalyst, they can collapse it down into one pass through the data, and then you actually get, this one doesn't have it, but like you would actually see it get pushed down into the physical layer. So here, I still have to read all the data, and then I'm going to apply the filter, and then I'm going to project it out and choose the columns that I want. The better way, I kind of had an example of this. Yeah, you would see that, like those 2 get collapsed into one, and that's where pushdowns are happening. Yes, I have a code example of it in my notebook. But yeah, there's kind of the overall Catalyst, some of the tricks it's doing, right? Pushdowns, constant folding, subquery elimination, huge. The cool thing is that you can create your own rules, right? You can actually hook in to like Catalyst, right? And yeah, these end up just being case classes and all the normal Scala things, right? Yeah, and so you can apply the rule to any stage, right? And that's typically you would pick the one that has the most information or the minimum amount of information that you need to evaluate. Other thing to mention, it was mentioned at the very beginning that Python plus old school RDDs is the absolute worst thing in the world. Don't ever just give up on Python, give up on Spark. Just don't even bother. You'll have a terrible experience. I think it was one of the DataFrames. I'm trying to think the worst week of my life at Databricks when that was, because we actually had to migrate all of our customers from Spark 1.2 to Spark 1.3. And we didn't have a multiple version, like a multiple Spark version of our product. So, whenever we upgraded, they had to upgrade also. So, we had to basically go through and just, highlight all the code that would break, and everyone's queries were broken. They've since fixed that, and now you can run multiple versions, and there's no forced upgrade path. But we saw this quite a bit, and so people had to, essentially just what would come out of SQL context, read would be what used to be schema RDD, but is now DataFrame. So by just adding .rdd to the end of the DataFrame, you would get back to the old way. That's just kind of an anecdotal thing. But, yeah, and so like that guy mentioned, when you're in DataFrame land, what you're building up in Python or R or like these other languages, these other bindings, is it's just the logical plan, right? So think of DataFrame as just kind of a holder for your plan, for the logical plan, which is like pretty basic stuff. So between Python process and the JVM, I'm just passing that, and then on the way back is just the results, right? Thanks. So if you can minimize, but you still have the problem if you do have a lot of results, that those results are going to come back and have to get pickled and serialized and back. So just keep an eye on that. There's a new concept called data sets that I heard about at the summit, which is similar to DataFrames. Not quite sure what Databricks is doing there, but there's something. I'm not going to keep you guys too much longer, but one thing that's really, really cool. It's cool because I worked on it. Yes, I actually worked on the Kinesis part of this, but Kafka. Have you guys used the Direct Kafka? It's called Direct Kafka, the actual API. So let me show you before. This is how Kinesis works. It's still kind of crappy, but it's a little bit better. Before Spark Streaming, you would have what was basically a single receiver. I mean, you could scale it out. If you had a multi-partitioned, like buffered streaming source, like Kafka, Kinesis have multiple partitions for throughput and that kind of thing, you would have multiple of these receivers, but you would still only have one receiver per partition. So single point of failure, these things should pop out in your head. Also, from a performance standpoint, so any data that was in flight had to get written out to a write-ahead log. Right? This is how like Cassandra and these kind of tools work, where they're getting data very quickly and just writing it to an append-only log for like durability. So each receiver had to do that, and then it would create the batch, and then basically be submitting a little mini batch job of just a 5-second interval or a 500 millisecond interval. So Spark was already optimized for those little micro batches, but this guy Cody, I think he's from Austin, Texas, came along and built this. So he was thinking about it one day and realized, well, why do I need to have a single guy that's pulling from each partition? I can actually parallelize this, right? And so because Kafka has deterministic offsets, so and it's all continuous and it's all incremental or increasing, you can actually just farm out as big as your cluster can be. So not just a couple that you've pulled out of your Spark cluster, but farm these out and tell each one just pull 100 messages, just pull some sort of interval. And so these can all happen in parallel. So back to one of the fundamental themes here about parallelism. So now, all of this processing can happen in parallel. The problem here, some of you might think about the ordering, right? Like you're going to potentially get things out of order. So one thing is lost my train of thought there on that, but so within a partition, you are always guaranteed ordering. But the second that you go outside of partitions, that's even worse. So that's where to have total ordering in any of these systems is really very, very difficult. You basically lose all of your performance if you're trying to total order. But I believe I can't think of the exact way that this ordering, because now that I think about it, this would be, but there's some way that that's not happening. But so the other benefit here is that there's no write-ahead log, right? So there's no need to actually pull things off, because if this node dies while this data is in flight, or while it's just about to submit a job, or it's just about to do processing, because these actually are jobs themselves. They're just sort of long-running jobs. It knows the start and the end offset, so it can go back and then restore from there. So the cool thing about that is that you're like essentially not building for failure, right? Like your hot path doesn't have failure in mind, right? Like write-ahead logs are like sort of like MapReduce, and where you're like always writing everything out and then having to pull it back in. It's because you're like assuming that something's going to go wrong. So you're affecting the whole overall happy path for this like relatively small number of unhappy failure paths. Back pressure, yeah, so hyperlog log. Yeah, these are really cool data structures. Yeah, Twitter has this library called Algebird that's used within Spark. There's streaming, like examples within the Spark code base that use like hyperlog log count min sketch from Algebird directly. Yeah, I wasn't sure if I should bring this up, but Monte Carlo simulations based in the atomic bomb era, Manhattan Project, but this law of large numbers is kind of the overarching theme here, right? Like the intuition and so this is actually part of the Spark code base, this Spark Pi example. Think of throwing darts or just kind of randomly picking so you can estimate pi by taking all so the thinking here is that this is a square, right? And so this is that's your diameter. So by taking all these red dots, dividing by the total dots, and then multiply by 4, you can estimate pi. So a parameter into the Spark Pi example is the number of darts, the number of trials. So if you do 10, you'll get 3.1. If you do, 10,000, you'll start getting closer to the real value. Yeah, I think that's it. Any question? I saw someone else. Yeah. Oh, yeah. For the throttling or for the back pressure? For the throttling. Yeah. So the question is about throttling. What was there before back pressure came along, right? So Spark 1. I think even Spark 1.3 might have had throttling as well. So the big difference between throttling and the back pressure is just dropping things on the floor, right? Like when you're throttling, you're just saying, can't take it. But back pressure pushes back, but that requires that the source can understand that. So I mentioned TypeSafe. So that's the company behind Scala. They submitted that feature for the back pressure. Yeah, so throttling, that was built by the same Databricks guy that runs the Spark Streaming project. That was just, that's simple. That's just over a period of time if more data is coming in. Right? And what's cool, so like we see a lot of Flume, right? People set up Flume agents and they're pushing logs in. And Flume has slowly been getting better and better about having transactional support and like the ability to act back and say, yes, I got this piece of data. So Flume's getting there. Yeah, the question is about, does Catalyst understand the physical configuration of your cluster? And I've never, just trying to reason through it, but I haven't seen anything on that. No. Mm-mm. The only physical plan optimization that happens is that auto broadcast, the map side thing. But I do know that the team lead or the Spark SQL lead I think once he's passed this basic Tungsten stuff, because this just kind of came out of nowhere and like every team had to start working on it. There's going to be some more cost-based stuff, but I didn't think about that. Right, like what other projects do that? Yeah, do you know other projects that? Yeah. Yeah. Right. Yeah. Yeah. Someone actually said this to me, I think, at the summit. I think it was one of the IBM guys. It was like, we keep, well, yeah, those DB2 guys know. Yeah. But we go through this every few years, and he can almost see Spark and Databricks bumping into all the same things that he bumped into 25 years ago, and that DB2. Yeah, I can't remember if he even worked for IBM, but yeah, he was just giving me crap about that. So yeah, that's a really good idea, and that's kind of the next level, right? It's being able to adapt to your physical runtimes. Yeah. I know that there was a lot of talk at the summit and sort of the meetups that were leading up to the summit about actually building to LLVM, so starting to actually take so that there's Reynolds and Matei and these guys, the main architects of Spark, the creators of it back in the day. Yes, I know Matei is working on that kind of stuff out at MIT. Yeah, he has his little, I guess, interns or whatever they are, working on that. Yeah, LLVM stuff, but I haven't heard any of that. Yeah, that's interesting. Yeah, you're all chatty in the beginning, and now you're... Questions? Oh. Yeah. The question is about this, right? Parquet and everything is all fine and dandy, and DataFrames are going to start to be able to read heuristics off of columnar data. But this came up a few times at Databricks and since where, because Databricks and Spark love Parquet. They do everything with Parquet. They store their machine learning model. They store decision trees with Parquet. They, for things that you wouldn't. But I think the thinking there is that because of the compression and because of a lot of things, it's not that bad. But yes, any typical machine learning case where you are going row-wise, right? You're plowing through training data sets and that kind of stuff. It seems like it would make sense to keep it row-wise, right? Spark is an analytics engine, right? That's kind of its main core. And I'm trying to think if there was any empirical, because I know the guy behind Spark SQL, that the same guy, Michael Armbrust, that is, he's always talking about more and more heuristics, more and more cost analysis. Just swears by Parquet and refuses to believe that kind of row-wise storage is better. But I think there was one customer where we had them try it out, but I don't even remember if I got the answer back, because it was just use Parquet anyway kind of thing. But what were you thinking? Specifically, were you thinking something along those lines? What would be a row-wise analytics kind of work? Yeah. Oh. I've been seeing that more and more. It's so hard to debug these. I keep an eye on the user list, and people always are like, DataFrames suck. They're so slow. And you were doing straight RDDs, just going through which language? You're doing everything in Scala. Because using DataFrames doesn't necessarily imply that you're doing things columnar, right? It's more the combination of DataFrames with Parquet or with a columnar storage format. I'd be curious to hear more about what was actually. So you're going, and how wide were these TF-IDF vectors? Oh, really? And did you look at the query plans that were being generated, any of the physical plans or anything? Did anything pop out? So your hunch is that the overhead of DataFrames wasn't worth it in this case, right? Yeah. Yeah. Right. Which version of Spark? Yes, one. Still the same problem too. I mean, I don't know why it would change. It'd probably get worse. Yeah. I know it's tough without seeing the workload. Yeah. The question is about when you're doing, so you're talking about the pair RDD functions, right? Like that are all key, like key value, right? Like group by key, that kind of stuff, right? Triggers something in my head about the way aggregations. the first iteration Spark. Was it Spark 1.4 when DataFrames came out? Like, was that the first time that you guys tried that? Was it 1.3? Something I remember changed between that would have been 1.3 and 1.4 for the aggregations. Yes, like you're not using any kind of UDF or anything in there where it would. I'm just trying to think what would prevent Catalyst from. Maybe try it with the new Tungsten stuff and see if there's any benefits from these byte buffers, because you can actually join byte buffers now, right? Which is totally crazy. So, and that way it doesn't have to deserialize the whole thing and reserialize it. That's all the Tungsten. That was one of the 200 things that changed, right? There's a Tungsten join or an unsafe join. I know there was some improvements to some of the quirkier left outer join, or there was one or two of them that were. I think that might have specifically been a broadcast join that was not the normal type of join, but I think that came in 1.5. But it doesn't sound like you're doing anything crazy like that, right? Yeah, if you can send me a code snippet, I would love to look at it. If you can just generalize something and send it, or just kind of roughly what you were doing. Because I've turned completely away from RDDs. I read this funny blog post where it's like if you're still writing to RDDs, you're basically writing bytecode. You're back to writing JVM bytecode. But then there's cases where no, totally right. So. Right. Yeah, something's got to be on your mind. Okay. Just thinking if traffic is light, you can make it home smoothly. Yeah. I was waiting for this all night. The question is about Flink. And unfortunately, I missed the Flink forward. Yeah, did you guys go to that? Did anyone here go to Flink forward? I think, yes, I meant to ask you about that. I think I saw that, actually, or I saw that, that you were speaking there. Yeah, so what are your thoughts on Flink? I don't really know it that well. Yeah, did you like that? It's like VHS versus Betamax. Yeah, it started off streaming, right? Yeah, I mean, just to kind of give you like in the States, it's up every now and then. Capital One Bank seems to be very vocal about it, but it turns out it's just one guy. He just has a lot of different blog posts and meetups, and he's a very chatty. I finally met him. He's like this crazy guy. He's pretty funny. Yeah, he's a very interesting guy, but I don't think they're actually using it. Like, I assumed Capital One was using it because this person was so vocal about it. But yeah, I mean, from a Spark versus Flink standpoint, it's streaming, Flink started off more streaming and then has been adding in more batch. We kind of make fun of them a lot for, like, we'll come out with a machine learning library, we being Spark. We'll come out with a machine learning library, and then 3 days later it's checked into their, it's the same code. Like, they're pretty open about it. They're like, well, we've been looking at multiple algorithms, and you guys had a really good one. Why would we not take it, right? So, yeah, I'm curious to see how that plays out. Like, the whole marketing thing is interesting. I've never actually seen any benchmarks, anyone comparing the two for any kind of workloads, which is interesting. Yes, I know Databricks hates benchmarks. Well, yeah, except ones that they produce, right? Like the Gravestart. Which we had never actually, at like IBM, we've tried to reproduce that. So wish that guy was here. That, like, with the same data set, with what we think were the same tuning parameters, we can't get that kind of performance. So we don't know what kind of magic they were doing, but yeah, I'd be curious to see if, and Flink is also Java only, right? Yeah, I don't think there's Python bindings or there's no Scala either. Right? I mean, it's like written in Java, right? Versus. Yeah, I mean, what do you think is going to happen? So it's more about marketing, like you think? Yeah. Oh, that's the other big difference, yeah. Like the micro batch, yeah. 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 So it's higher throughput, because you're batching, the, classic. You can batch more, the more you can jam through the processing engine versus, so people used to compare Spark streaming and Storm all the time because it's the same comparison. Storm is single record or single tuple, going in, and so like the whole, for one particular tuple, it's going to be lower latency because it's going to get through that pipe faster than if you have to batch everything up. And overall throughput goes down. And then I guess the other big argument against Storm, you basically need Storm plus, what's it called, like Trident for the like transactional type stuff, for like recovery and right, like guarantee, right, like delivery guarantees, right, like the whole thing about at least once, like delivery and all that. So, this is something else to mention about Spark. Spark is like the new Kafka, or like the new Kafka stuff, and or like Kinesis support claim to be once, right, like exactly once, or like delivery guarantee, but that's not really true, and it's not really Spark's fault. It depends on. It can pull it off the pipe in an exactly this manner, but the second that it's trying to write to a database or something beyond its control fails, you don't really, like, there's nothing you can do. It could be possible that it would get rewritten. So you always have to factor in idempotency and that kind of stuff. Yeah, I think the other thing too about Storm is. There was the guarantee, and then isn't it written in like Clojure or something too? Like some crazy. Yeah, do you guys use Clojure probably? Yeah, I love Clojure. There's a lot of people, especially in California, because they've been on to streaming for so long that there's a lot of shops, like Twitter, for example, just like rewrote Storm. I think it's called Heron, Heron. It's not open source, and I don't think they plan to open source it. But they had so much investment in Storm because of like Nathan Mars and like the guy that like built Storm, and then like Twitter bought them. That they couldn't. They like had all these APIs, so they had to maintain the API like compatibility. But they knew that no one really else cares about that except them, kind of thing. So, and then they just swap out the back end and put in this new Heron. Any questions from the remote audience? If you're out there watching, please hit *6. Where will it'll show up here? What? Whoa. *6.
Test. Yeah. So please hit *6, and then you can ask questions.
Yeah.